This is the Measuring Links and Buried Pipes team sponsored by SoCalGas.
Thanks, Mike. Hello, everyone. Thank you for tuning in today to watch our presentation of our project. It is a pleasure to have all of you here. We are Team 34, Measuring Leaks and Buried Pipes. I'm joined with my teammates, Zach Benavides, Brandon Hernandez, Astrid Rodriguez, Alfonso Suarez, and myself, Alexis Rios. We would like to thank SoCalGas for helping us out throughout this year-round project, and specifically our liaisons, Jerome Powell, Daniel Lopez, and Ricardo Vargas. We would also like to thank our lovely advisor, Everardo Hernandez, for helping us out here on campus. Next up, we have our team organizational chart. We have Jerome, Daniel, and Ricardo helping us out throughout the year with technical help, such as testing at the SoCalGas facility, and Everardo helping us out at school in variety of areas, such as design concepts. We have Astrid, our team captain, which keeps us on our toes to help us meet deadlines. Zach, the design engineer, Brandon and myself as support engineers, and Alfonso as our computational fluid dynamics engineer. Next up, I'll be talking about the background and statement of work. The main purpose of this project is to do field testing, to capture and measure natural gas leaks that occur from natural pipes that may need maintenance. On the image on the right, the apparatus captures and directs the mixture of air and methane emissions to the high flow sampler and methane detector. These measurements are then recorded to quantify the leak from the buried natural gas pipelines. For example, if there's a suspected leak in your front lawn, a couple of tasks would be recorded by moving the apparatus around the lawn. With that data recorded, the crew can approximately dig and do the maintenance on the line. Moving on. Here we have the current apparatus of the SoCalGas system. As you can see on the left, the image displays an apparatus where there's a lot of piping. This kind of system causes a lot of eddies within the system and increases the time it requires to get appropriate readings. On the right image, you can see the tarp and chain added. The tarp is used to conceal any openings that might be present around the rim of the system. The chainmail helps to close off those leaks. We will then show the changes that we have made to our design to fit SoCalGas requirements. Following up, our system has to remain compatible with previous tools, being the quick disconnect hose that connects to our system through the quick disconnect coupling, then over to the high flow sampler that runs at 8 cubic feet per minute, or CFM, and finally over to the gas measuring unit, or GMU, which measures in parts per million, known as ppm, or lower explosive limit, known as LEL. In regard to the statement of work, SoCalGas has a need to measure gas leaks from underground lines because they are not desired by the customer or the business. Also, we were assigned to design and build a portable enclosure that meets the requirements given, and we would be able to capture and measure the emissions into an existing pump and gas measuring unit. Now, I'll pass it on to Brandon, in which we will talk about the requirements and design concerns.
Thank you, Alexis. To start off, I'd like to point out the header row and what each column represents. The first column represents the title, followed by requirements, source, method of verification, and whether our requirement was met. It was required that the overall weight of the enclosure needed to be less than 40 pounds. Our enclosure met this requirement by having an approximate weight of 11 pounds. The second requirement was that the compacted size of the enclosure needed to be less than or equal to the following dimensions: 2.5 feet in length by 1 foot wide with a 1.5 foot height. This requirement was also met with our enclosure having a compact size of 1.67 feet in length by 0.625 feet wide with a 0.625 foot height. Third requirement was that the deployed size of the enclosure for when it is in use should be 4 feet in length by 4 feet wide. Our enclosure also met this requirement by having a deployed size of 4 feet length by 4 foot wide with a height of 1 foot. The fourth requirement was the durability of the enclosure, which meant that it needed to be robust and resistant to various weather elements. Fortunately, we were not able to verify this requirement, and it is to be determined. Moving forward, the fifth requirement was the compatibility of the enclosure. This simply meant that the top of the enclosure need to be compatible with the quick release that connects to the high flow sampler. This requirement was met as we were able to attach the quick release to the top of our enclosure. The sixth requirement was isolation, which meant that the base of the enclosure needed to create a seal to prevent any unwanted air from coming into the enclosure. This requirement was also met by the use of homemade sandbag rolls that were placed at the base of the enclosure. The seventh and final requirement was the internal pressure, which meant that the inside needed to maintain ambient pressure at all times. Fortunately, we were also not able to verify this requirement, and it is to be determined. Moving forward, the first design consideration was that in cases where multiple measurements need to be taken, the shape of the enclosure should allow for grid line sampling. It also should allow for full coverage of the area that is being measured, and it should prevent any overlap as the enclosure transitions between measurements. The image on the right is a simple demonstration of what grid line sampling looks like. Moving forward. The second design consideration was considering having a minimal volume of the design and also the choice of the geometric shape of the design. The purpose of the minimal volume was to assist with achieving a quicker time for a steady methane reading, and the purpose on the geometric shape of the design was that the shape should limit dead spaces that can cause swirling eddies, trap gas, and disrupt the flow as it transitions from the inlet to the outlet. The animation on the right is a simple demonstration of how a swirling eddy behaves. Moving forward. The third design consideration was that since the enclosure is going to be used outdoors and it is going to be used on the ground, it is important to consider that measurements can be taken on different types of terrain, and also that the ground that is being measured is not always going to be leveled or flat. Moving forward. The fourth and final design consideration was that the inside structure should remain at ambient pressure. It should create a good mixture between the ambient air that is entering our enclosure with the methane that is emitting from the ground, and it should avoid vacuum behavior, as this can possibly cause the enclosure to collapse and also create error in the data that is being obtained. Taking all these design requirements and considerations into effect, Zach will go ahead and discuss the team design.
Thanks, Brandon. Thanks everyone for being here. So yeah, we took all those requirements into consideration along with, what we were actually capable of building. And we decided the best geometry is a four-sided pyramid. It keeps the square base while reducing volume. A pyramid like this has 1/3 the volume of a similar sized cube. We also eliminated a rigid bottom structure by using extendable legs like a tripod. This will allow for better isolation because the fabric edges and sandbags can conform easily to uneven surfaces. So the main enclosure, we basically broke it down into 4 substructures. And the first one I'll discuss is the box and hinges at the top. Firstly, you can see the quick connect coupler at the top there. That's attached through screws through the top plate. When we're designing this, we also had to take into consideration our manufacturing capabilities at Cal State, Los Angeles. In doing so, we figured laser cutting 1/2-inch thick slabs of acrylic to create the box was our best bet, and we could do it most accurately. The slabs would then be cut and then screwed together, and we chamfered off the corners to attach the hinge assemblies. Those hinge assemblies would be 3D printed. And you can see in our picture here at the bottom layer is a flow conditioner that we were designing. Now, if we flip it around, look at it from the top, you can see the 4 hinges on the corners. And you can see the perforations for the flow conditioner. The cross-sectional area of those does equal the outflow hole, which connects to the quick release. Our hope there was that the flow conditioner would create a more streamlined and laminar flow for quicker testing in the methane detector. The next subsystem is the legs and cabling. So the aluminum telescoping legs and the plastic snap locks, we bought those from a vendor. They are very lightweight and very strong. The cabling, that you can see there going from snap lock to snap lock. That is 1/8 inch vinyl coated steel cable, and it's cut to exact lengths. The ones on the bottom are 3 feet and the higher ones are 2 feet. They have two purposes really. First, it helps create structure by limiting the splaying out of the legs and keeping it in the square configuration. And it also helps add strength to the structure. And the second is that the cabling is going to be used to attach the fabric to the structure. The leg sections, we cut them to the appropriate lengths so that each extension grows the base of the perimeter by 1 foot per side. So as you can see there, when all 3 of the tubing sections are fully extended, it is a 4 foot by 4 foot perimeter. You retract the outermost section, it becomes 3 by 3, and then 2 by 2, and so on. The next subsection is the tarp. And for this, we went ahead and purchased a 1.3 ounce silicone and urethane impregnated ripstop nylon. It's basically parachute material. It's extremely lightweight. It's very strong. I was not able to tear it with my bare hands. And it has 0 porosity, so it's great for working outdoors. The rain won't affect it. And we did some temperature testing, and we determined that to reduce heat and therefore pressure of the system, we would go with the color white. Also, you can see there the loops. These loops are the same ripstop material. They will be glued to the main tarp, and those are what the steel cable will be threaded through, and that is how the tarp is attached to the structure, to the frame. At the bottom there, you can also see 6-inch flaps of material that we left on there to help create the seal at the bottom. And the last subsystem is the peripherals. These are not actually attached to the structure itself, but they are part of the design. The first being the sandbag snakes. These are made of the same material. They can be filled with sand. Actually, with the prototypes that we managed to build, we filled them with rice, and those work great. And there's also the clean air intake. That is bringing the clean air into the system to prevent the negative pressure on the inside. And it'll come to a T-fitting, which will disperse the clean air into the structure evenly. And to talk more about the fluids of the system, I'm going to go ahead and pass it over to Alfonso.
Thank you, Zach. Now, as previously mentioned, the entirety of testing will be done outdoors, as the enclosure is meant to help quantify methane flux coming from underground. Therefore, a lot of the times, operating parameters will be based on environmental conditions during the time of day during the testing. Such cases will be such as solar radiation, material properties, temperature, gravity, other things that will basically be affecting how the gas particles will behave inside our enclosure. However, there will be 2 constant conditions, one being that of our clean air inlet, which will be acted on by environmental pressure, and secondly, the outlet directed to the high flow sampler, which will give a volumetric flow rate range between 6 to 8 CFM. Now, taking all this into consideration, the team needed to find a way to analyze the mixture that is not visible to the human eye. Therefore, we went ahead and utilized the SolidWorks flow simulation interface. This allowed for us to study the fluid dynamic occurring within our enclosure while allowing us to recreate the inside geometry. Now, the software was utilized in the following breakdown, where first we went ahead and wanted to test the mixture within a general shape, which would then be later optimized through various testing parameter simulations. Lastly, the design will be placed under lab and field testing simulations to see how the fluid trajectories will be. Now, moving forward, we can see how we went ahead and tested for air mixture using CFD on general design ideas, which led us to our final setup. Now, as we wanted to keep the square base for our design, we went ahead and tested the following geometries that would be possible to be manufactured in a way that can be collapsible. Now, using the 2 known conditions, we went ahead and ran our simulations. However, it should be noted that the reason for not introducing methane yet to these simulations is because the density of methane gas is near half that of air. Therefore, through our design shape, we hope to allow for the natural flowing air to be the catalyst of our enclosure, assisting the rising methane flux from underneath the ground to travel into our outlet sampler. If we look below, we see the standard cube enclosure allowed for a buildup of particles to occur on one side, which is something we want to avoid happening. Now, on the other hand, you have a uniform mixture occurring within the pyramid design, therefore supporting why we moved forward with the design. Now that we have a general shape in mind, we went ahead and saw how it could be optimized. So when optimizing the shape, there was plenty of concerns on how the enclosure setup will affect its fluid dynamic. When considering the setup, such factors as the type of fittings, the number of fittings, or even size, shape, and locations needed to be considered, as the goal was to find an efficient fitting setup that will allow for a uniform mixture inside the enclosure, given that all we're going to be using will be natural flowing air. So aside for our goal being our mixture, there will also be certain things we wanted to avoid, such as having a forced airflow entering our system or not allowing enough flow, which in turn will create a vacuum effect. Therefore, after various simulations, the following setup was used. We went ahead and used a 1 foot high with a 1-inch diameter T-fitting, which moving forward, we'll see how the geometry went ahead and was used under these simulated testing. So through simulations, we could go ahead and see we mocked our parameters as best as possible as those taken at our liaisons facility. These included a 0.017 CFM methane inlet under our system, which will simulate the underground methane flux. Additionally, the effects from the high flow sampler and clean air intake were also taken into account. As we could see, we would have air mixing within our system that shows that even at a low intensity acting parameter, we are still seeing a mixture occurring within the system. It should be noted that the results show readings near to equal the amount of the methane leaving the system to what was being pumped in, justifying uniform mixtures while avoiding trapped pockets of methane. But as mentioned, actual field testing will be done outside, as it is needed to help quantify leaks. Therefore, moving forward, we can see how a simulated test for a field testing day will look like. Now, in this simulated scenario, we wanted to observe how our final setup will act in our real field tested conditions. Now, this is where those initially mentioned operating parameters will come into play, such as that of the solar radiation and our surface material. These conditions are creating a more intense effect on the enclosure, which is what we're expecting to see in actual testing. Given that most methane fluxes measured outdoors are relatively low, we went ahead and simulated a low flow rate quantity entering at different locations of our system, as to better simulate a randomness of methane fluxes from underneath the ground. Now, the biggest factor that will be affecting our system will be that of solar radiation. Therefore, for this simulation, we went ahead and accounted for the most extreme case, which will be that of a black body wall. However, even though we still see that through our simulation, we do have an even mixture between the entering blue air particles, which will be that of our air, and that of the underground methane flux being represented as our red particles. Now, the simulated results show that the enclosure worked better in terms of actual mixing when a higher intensity parameter was affected, which supports our design enclosure. Moving forward, I will pass it along to Asher to give more of a background of how the team conducted testing of our prototype at our liaisons facility.
Thank you, Alfonso. So with the time allowed, we were able to build and test 2 prototypes. With these, we took it to the SoCal gas facility, and we tested 2 different heights. We built one of 18 inches tall and the other one of 12 inches tall. They were both with 4 feet by 4 feet square area at the bottom. The purpose of this test was to find the geometry that would reach a steady reading the quickest. The picture shown is our final prototype of 12 inches tall. So starting on the left side at the top, there's the hose that leads to the high flow sampler and the methane reader. The sandbags were put around the perimeter to ensure a seal, and at the bottom, there's a 1-inch diameter pipe for ambient air intake. At this inlet, there is a reader to ensure that the amount of methane concentration going into the system it's coming from the ambient air. So this value is subtracted from the final reading to ensure that the measurement is only from the enclosure. The arrow at the top points to a small tube that simulates a gas leak. So this ensures that we're dealing with a controlled system. Moving forward, on to the next slide. This shows a diagram of the open system that we are dealing with. There are 2 inlets and 1 outlet. One inlet is from the ambient air to ensure that there's no vacuum formed within the system, and the other inlet is a gas leak. The tested parameters were of 0.017 cubic feet per minute, or CFM, and 0.042 CFMs. The high flow sampler gives an outflow of 6 to 8 cubic feet per minute, and the methane reader reads an outlet concentration in parts per billion. When the simulated gas leak is 0.017 CFMs, the desired reading we're looking for is 1900 to 2100 parts per minute. So moving forward, we recorded the data and we graphed it. We graphed it against time to find which of the two prototypes reached a steady reading the fastest. The blue dots are the 18-inch prototype, and the orange dots are the 12-inch prototype. The yellow area is the desired concentration reading we are looking for. The line fit is the moving average, which just made it easier for us to see a pattern in our data. Although the 18-inch prototype seems to reach a desired reading the fastest, it shows a wider range at which at a later time moves away from the desired reading. So moving forward, we'll take a closer look. So now we're looking at a zoom in of the graph when it reaches the stated reading. After 240 seconds, which is about 4 minutes, the 12-inch prototype is within the range with a tighter threshold compared to that of the 18-inch prototype. So we took all this data and we analyzed it and compared with our flow simulations, and we determined the final height of our design. Moving forward, so in conclusion, we were able to design an enclosure apparatus that exceeds the requirement given to us by our liaisons. We had a chance to test these prototypes and show that they reached the threshold requirements of flow and of operation. Not only were we able to test our design, but we were also able to support it with computational fluid dynamics simulations. All of the components to build our final enclosure were gathered. So if we were to keep going with this project, the next steps that we would take would be to build our final enclosure assembly and to take it out for field testing and to gather more data. We would like to thank our liaisons at SoCalGas and Pico Rivera, Jerome Powell, Ricardo Vargas, and Daniel Lopez, also all the technicians, the senior design coordinators, instructors, Michael Thornburn and Christopher Bachman, our advisor who helped us out a lot, Everardo Hernandez, and also the facility at Casa de Ley Makerspace. Does anyone have any questions?
Okay, thank you. So the floor is open now for questions. If all you have to do is unmute your microphone and ask away. Is there a first question?
Yes, can you hear me?
Yes.
This is Ray. First of all, thank you very much to Brandon, Zach, Astrid, Alexis, and Alfonso for getting through this under very difficult circumstances. And I'm applauding. I hope you can hear that. I personally really appreciate this. So did you consider like a dome? I know you mentioned the word dome. Did you consider a spherical type of shape as opposed to, linear type deployments that you had?
Yes, so we went ahead and considered a dome hybrid with like a rectangle in a sense, because we still wanted to keep that square base bottom. So the dome, when we tested the CAD simulations on it, we're seeing that we're having too much of a little pressure buildup inside. So which is why we went ahead and eliminated that one from our choices. And we went forward with the cube or pyramid design, since those two could be easily manufactured to be collapsible and still had that square base bottom that we seeked for.
Yeah, the dome was obviously one of the first things that came to our mind as well, because, it seems like it would have a natural flow that would go through it. Two of the issues that we came across were to make an actual dome, it required increasing the volume more than the pyramid did. Mm-hmm. And the actual engineering, the manufacturing of the dome was much more difficult than just creating the pyramid.
It would be very much more difficult.
Yeah.
Okay. And did you do formal statistics? You got to steady state for both designs. Did you do formal statistics in terms of mean and standard deviation? Or did you just kind of eyeball it and say this has less variation?
We just kind of eyeballed it from what the graph and what it looked like. we were not able to get to that point to do mean statistics.
Okay, thank you.
I had a question. Did you have any requirements for ease of assembly or disassembly?
No, we just had it, just needed to be required to collapse to fit the trunk of a standard car. And they just required that it had that 4x4 to ensure that they're covering the majority of the area. But they didn't really mention anything about ease. But
Okay.
they did mention just as long as it's fulfilling that 4x4 base frame, and also that they're able to collapse it and fit it in
I can jump in.
the standard trunk.
They did. It wasn't a formal requirement, but they did. You know, we actually went to the facility and they had us set up their current apparatus, and they took great joy in pointing out how long it was taking us to do that. so they did infer that they would like something that was easier and quicker to set up, which I believe that we absolutely met.
How long did it take you to set up?
5 minutes, like laying everything down.
To drag the thing out there, set up, connect the hoses, put the tarp, drop the chain around it, connect the backpack and everything like that. And that's for one testing. Whereas like we were talking about the grid line testing, if they had to do that, they would have to pick up, move over the 4 feet, set up, test again.
So
Without having actually built ours, you know, we couldn't actually do a time testing, but ours should be, it's all contained. So hopefully it should be much quicker.
okay.
Well, our prototype it's similar to our final design, and setting the prototype up just took like 10, 15 seconds. So comparing the time it took us to set up their equipment to ours, it was gradually easier to set up our prototype.
Oh, very nice.
Other questions?
So I have so nice job, team. I liked your balance of analysis and manufacturing and testing. It was cool to see, even considering the circumstances, you guys got a little bit of everything. And so congratulations to all of you, and Everardo, another good project. I'm kind of curious. So, I mean, it seems like this, you know, a lot of the things went well. So what are your guys' and gals' next steps for the project? Are you going to hand it off, or the Everardo is going to put the finishing touches on it? You know, it seems like there's a lot of potential here. What's the plans going forward?
It's a good question. I mean, I think I speak for the whole team when we were very disappointed. We were so close to being able to actually construct this. It's very tantalizing. And we have a majority of the materials we would need to build it. Much like everything else in life right now, everything seems to be pretty much up in the air. So not sure, quite honestly.
And it is nice to say from me that we were like a week, just a week behind building that square top on top of the pyramid, because we had the drawings already by then. So this team really exceptional. Of course, while I was pushing them and they respond, and that was super. I mean, you always push until you push back, they push back, and then you cannot push anymore. So this team did very, very good. I mean, I'm very proud of everybody, and thanks to the Makerspace also for providing us like the facility to meet and to, you know, update every Friday, working together. And most of the team got on time, and we met, and I believe we did it. You guys did it, actually. Thank you.
Thanks, Everardo.
May I ask, why did you go from a chain to sandbags?
It was significantly lighter, and since it's 4 sections, it's easier to carry. The chain was, you know, it was very heavy and kind of difficult to handle. Unlike the sandbags, I could just put over my shoulder and carry something else. It was more easier to transport.
Also very, very malleable around the rough edges. So like if you were to test around a curve, you can just like lay the sandbags or ice bags around, which would create a better enclosure.
Okay.
One question. First of all, good job. And what software did you use for the analysis?
For the analysis, we went ahead and used the flow simulation interface on SolidWorks. As through that, we're able to mock the inside geometry of our enclosure and then add different parameters to the simulation and see how it will affect it.
Okay, so the school provides that license?
Yes, they provide the SolidWorks license, and then the flow simulation interface is like an add-on to it. So it's all part of like the bundle package, I guess you could say. So you'll be able to do simulations with the school licensing.
Okay, very good.
Any other questions? Okay, if not, well, congratulations, team.
Professor Thorburn,
Yes?
I just want to say thank you very much to Brandon, Zach, Astrid, Alexis, Alfonso, and Professor Hernandez for doing this under very difficult circumstances. I know you wanted to get much farther than you wanted, but it's okay. We're all dealing with difficult circumstances. We really appreciate it. We hope you learned a lot during these difficult times.
We did, and thank you for being here, Ray. You're a familiar face at this point.
Yes.
Okay. Well, thank you. And it was a good job.
Quick question. I know you recorded. Is there a way we can obtain the recording of it?
Yes, I'll let you guys, everybody know about how to do that. I'm working through the details right now, but that is the point.
Thank you very much.
Okay. All right. Well, thank you very much.
Thank you.
Everybody.
Thank you.
We'll see you all. Good job, guys.
Thank you, Roberto. Appreciate it.
Please stick around. The next presentation will begin in about 4 or 5 minutes. It's the robot odometry presentation, which is a Raytheon sponsored project.
And Professor Thorburn, I'll be back a little bit later at 5:20 for the SIA presentation.
Very good. Thank you.
Okay, good to see you again.
Goodbye.
Stay healthy, everybody.
Mhm.
Okay, let's see. We have Ismail's on, I think.
Yes, sir.
And
Yeah, I'm
Young?
on too.
Oh, good. Somebody's already taken over the screen. Young is here.
Yes.
Angel.
Here.
Angel's here. Edwin.
Yes, sir.
All right. And Jorge.
Yes, I'm here.
Awesome. Looks like the whole team is here. So we'll just wait a couple of minutes. I don't see your sponsors online yet. Except now we've got 3 people in the waiting room, so maybe that's them. We'll get started in just a minute or so. Here comes one of your sponsors.
Sounds good.
Hi, Robert. You're muted, but that's okay. Okay, well, it's about 2:40. Everybody on the team is here, so we can go ahead and get started. Welcome to Expo 2020, our first virtual Expo. We've got a full complement of presentations today. This will be going on. This sequence of presentations will go on until 6 o'clock. There's also computer science and civil engineering and technology presentations on other links. Welcome and thank you for coming. The format is we've got 40 minutes for this to take place. We expect the presentation to last about 20 minutes. There'll be then a period for questions and answers. And then at the end, we'll wrap things up and get ready for the next presentation as well. There should be ample time. So without then further ado, let me introduce the Robot Odometry team, a project sponsored by Raytheon Corporation.
Thank you, Professor Thornburg. Good afternoon. My name is Edwin Rashidian. I am the team lead of the Capstone Senior Design Project called Robot Odometry, sponsored by Raytheon. The team consists of Jorge Vicente, Ismael Garcia, Young Lo, and Angel Montejo. Our advisors are Dr. John Jacobs and Mr. Bob Dempster. Today I will be introducing our project that we have been working on over the past 2 semesters. Then I will hand it off to Jorge, to which he will be speaking about the system overview. After, Jorge will pass it over to Ismael, and he will be speaking about the interface architecture, and then pass it on to Young to speak about the mechanical design. And lastly, hand it over to Angel, who will be talking about the team's budget and results. The scope of the project is to take the existing autonomous robot and add on an odometry system that will track the traverse path of the robot using various electronic sensors that were picked for the design through thorough research and the softwares and algorithms that correspond to the electronics that the team had determined are best suited for this project. Odometry is the use of sensors to estimate the change of position over time. And for this project, we will determine the position of the robot when it is deployed in an environment where a human access is not feasible, such as a dangerous situation. The dangerous situation can be anything from an earthquake to a hurricane. The major problem that our team had come across, like everyone else in the world, is COVID-19. COVID-19 prevented the further development of our project by eliminating all access to vital resources on campus that are important for our project to have been completed. Also, the mandated social distancing prevents our team from collaborating, implementing, and testing our individual systems together. The objective of our project is to track the distance of the robot over time, while measuring the real-time position of the robot in X, Y coordinates. where X is the east heading of the robot and Y is the north heading of the robot. The measurements would be transmitted wirelessly to a mission computer and plotted on a map in real time, while having a total elapsed runtime of 15 minutes on one full charge of battery. The project requirements are as follows: location mapping in real time, robot runtime of 15 minutes on one full charge, and obstacle avoidance to be autonomous and avoid any obstacle size at least 2 by 3 inches. And now I'd like to hand it off to Jorge to speak about the system overview.
Thank you, Edwin. Now we will transition to our system overview and what it comprises of. Our system follows by first setting up our mission computer and plotting system, followed by powering on the robot and connecting through Bluetooth in order to enable or disable the robot's odometry and obstacle avoidance system. The motor, the obstacle avoidance system, and the odometry system will idle until the user enables all systems through Bluetooth. Once the user enables the robot system, it will begin its course. The robot will begin its obstacle avoidance system to detect any objects on its path, which then distance data will be collected as it starts changing position through its course. It will transmit this data to our mission computer, in which our mission computer will process the received data and begin plotting the data acquired in X and Y coordinates. This will be repeated through its course until the user disables the robot system, which concludes our robot's task. Now that we have gone over a system overview, we will now look into the subsystem put together for this project. First, we have the odometry system, which consists of BNO 055 inertial measurement unit, also referred as IMU for short, followed by 2 optical encoders that go into each sensor wheel of a robot. Lastly, our RFM95W LoRa radio frequency module as our transmitter for our robot. Our second subsystem is the mission computer, which consists of a laptop PC, which displays location of robot. Connected to this laptop PC, we have the PSOC6 microcontroller that processes our data for plotting, followed by another RFM95W LoRa radio frequency module as our receiver, which acquires data from our transmitter. Now we will discuss what each electronic component does in our odometry system. The optical encoder serves to calculate distance traveled by the robot, in which the BNO 055 IMU will track angular rotation for when the robot makes turns when avoiding obstacles, which then that data will be collected to be sent through our RF module transmitter, finally being received to our mission computer, where it then will be plotted. So how does the optical encoder track our distance? It does it by first tracking the number of revolutions the wheel has turned over time, which is shown in figure 1. That is calculated by 20 open and 20 closed slits on the encoder disk shown on figure 2. The optical sensor shown on figure 3 will output a pulse signal for every transition either open to close or close to open, which then generates a total of 40 pulse signals. Knowing that 40 pulse signals can be generated per wheel revolution, we can use the equation below to calculate our distance traveled. Following, we have the inertial measurement unit, IMU. The IMU we implemented into a robot was the Adafruit BNO 055 as shown on figure 1. Looking at figure 2, we see the angle theta, which represents the robot's turning angle, and it is according to the heading at the beginning of the turn. The BNO 055 is capable of measuring absolute orientation, but due to our project's design, we will only be measuring the heading angle. Now I will hand it off to Ismael Garcia, who will be elaborating on our interface architecture.
Thank you, George. For our wireless data transmission, we'll be using the RFM95W long-range radio module. It's communication protocol is SPI. It has an Arduino-based shield, so it can be mounted on top of the PSOC as seen on the picture to the right. And we are using the 900 megahertz radio version, so there would be less interference with Wi-Fi and cellular devices. Next slide, please. For the encoder and IMU task execution, we only want the encoder to read for a pulse when the robot is moving in a straight path. So we'll have the IMU activated at all times, and when the IMU detects a turn, it will be the trigger for deactivating the encoders momentarily, and it will reactivate them when there is no change in rotation. This will eliminate the problems due to the difference of the turning radius of the inner and outer wheels of the robot. Next slide, please. This is the flowchart that we're going to be using for the encoder and IMU task. First, we'll initialize the variables, and then we'll read from the IMU to measure for its angle and degree. Next, we'll have the encoder read for any pulse, and for every pulse the encoder reads, it will increment the number of pulses by 1, and then we'll delay the process for 10 milliseconds, and the loop will repeat. Next slide, please. As for the flowchart of the data transmission task, we'll first initialize the variables, and then we'll calculate for the distance that the robot has traveled and set it equal to d. Next, we'll convert the polar coordinates d and degree to a rectangular x and y. And then we'll set the number of pulses equal to 0 because we'll be accumulating the position data of x and y. Then we'll create a series of values for x and y and transmit the data to the receiver on the mission computer via the RF modules. Last, we'll delay the process for half a second so we can eliminate redundant values, and the loop will repeat. Next slide, please. Here are the equations we'll be using to track the robot's position over time. For the first equation, the distance is equal to the wheel circumference times the number of pulses the encoder has read, and divide that by 40 for the number of pulses and 1 wheel revolution. And the equations on the right are the conversions of polar d and degree to rectangular coordinates x and y. Next slide, please. For our mission computer, we'll have a receiver waiting to receive data from the transmitter on the robot. Once acquired, the data will be sent through the serial port, and the serial port will then read the data onto our Python IDE, where we'll store the data and use libraries provided by Python to plot it in a 2D x and y plot. Next slide. And now I'll hand it over to Young, who will talk about the mechanical design.
Thank you, Ismail. Today I will be talking about the mechanical structure of the robot, as well as showing how we will attach the sensors that we'll be adding to the robot this year. For our choice of computer-aided design program, we used SOLIDWORKS 2019 to model the housings for the sensors. We created housings for all the sensors needed for odometry, such as the IMU, optical encoder sensors, and the housing, which will contain a PSOC 6 and the receiving LoRa RF module. Next slide, please. Here's a comparison of the odometry robot versus the LoRa robot. The odometry robot shows the new sensor attached to the robot. On the odometry robot, we can see the IMU on top of the robot, the LoRa attached to the PSOC 6, and the encoders on the side of the robot. Next slide, please. And here are the sensors that we'll be attaching to the robot. The IMU will be placed on a platform. The LoRa RF module will be placed on top of the motor driver of the robot. The optical encoder sensors will be attached to both sides of the robot. Next slide, please. The encoder housing is used to support the dummy wheel and will be attached to the left and right side of the robot. The optical encoder sensor is attached to inside the housing, and this will provide a clear reading of the encoder pulses. Next slide, please. The IMU is placed on a high housing platform so that it can be screw tight, and the platform on the right is used to place the IMU at a higher level so that it can avoid magnetic interference that is generated by the electric motors. As of now, we have not done any testing to find the distance of the electromagnetic field generated by the DC motors, so as of now, we have just placed it on a higher level than the rest of the components. Next slide, please. We 3D modeled a PSOC 6 and RF module housing to hold the electronic components. This will further reduce the wiring clutter for the user and will protect the receiving end of the LoRa radio frequency module and the PSOC6 inside. And due to COVID-19, the housing for the PSOC6 and LoRa RF sensors could not get 3D printed due to the lack of resources. And next, I will be handing it off to Angel, who will elaborate on the project budgets and results.
Thank you, Yang. My name is Angel Montejo, and today I will begin with the topics of budget and results. Next slide, please. For the team's budget, we were given $300 at the start of the year. With that money, the team spent $198.86, leaving us with $101.14 left to spend. With this money, we bought all the essential items needed throughout the year, which includes the optical encoders, inertial measurement unit, and RF modules. In addition, we also purchased some extra equipment such as ESD straps, fuses, and a power cable to charge the batteries on the robot. Finally, all the 3D printed parts came at a cost, which came out of the senior design budget. Overall, we stayed within our budget and had room for extra components had it been necessary. Next slide, please. For all the electronic components, we have two images that show all the components on the robot and the mission computer. The parts included on the left for this process will be the PSOC6, which serves as our robot, one LoRa RF module, one serving as a transmitter, a second PSOC6, which serves as our data collector for the mission computer, and finally our mission computer, which will map the data being decoded from the PSOC. It is through the encoder disk on the robot that we will be collecting the data created as they rotate along the wheels and send data back to the PSOC6. Then from the microcontroller, our RF transmitter will be connected to the microcontroller and wirelessly transmit data to our second RF module, which will serve as our receiver. On the right, we have our second RF receiver, which will be connected to our PSOC6, which will serve as a data collector. Then finally, it is through the PSOC6 that will be connected to the mission computer and decode the data to display the location of the robot. Next slide, please. For our projected results and data, we have a simulation image showing how the final results looked for our odometry system. All the data collected was mapped on the mission computer using PyCharm. The mapping was the data collected from the LoRa RF modules and PSOC6. The open source library that we used with matplotlib, in which the plotting gave us a simulation using MATLAB syntax. These coordinates are plotted on an X and Y plane. One thing to note is that an X and Y axis will always be different depending on how the robot is placed on the ground. Wherever the robot starts its route, it sets its own Y axis as a starting point. The scope of this project was only to work on an X and Y coordinate system. Next slide, please. For our accomplishments, we started off the year by conducting research on which parts we needed to implement into our odometry system. Since then, we finalized our system design to meet specification requirements. Through our research, we discovered that we needed to implement an IMU and encoder into the robot to collect the data, which we successfully did. In order to incorporate the IMU and encoder, we had to make modifications to the robot. These modifications were done by 3D printing the housing for the encoder disk and incorporating two dummy wheels to support the encoder housing. For the IMU, we created a platform to place it above the robot in order to reduce the effects of the electrical noise from the IMU being close to the DC motors. And lastly, we successfully tested open source libraries for Python and plotted the X and Y coordinates of the robot using matplotlib. Next slide, please. Although we were able to successfully program all the electronics individually, we were unable to integrate all the electronic components to work together due to the virus health measures from the state leading to school closure. And even though we successfully 3D printed all our parts for the robot and their respective components, we could not install all the parts onto the robot due to the school closure. Next slide, please. We would like to give a special thanks to Raytheon and both of our advisors, Bob Dempster and Dr. John Jacobs. They met with us every week throughout the year and led us into the right direction when designing our robot. We owe it to them for their time and dedication for getting us to where we are today. Without their guidance, this project would not have been possible. Thank you. Any questions?
Okay, thank you, gentlemen. We have plenty of time for questions. All you need to do is to unmute your microphone to ask a question. Who wants to go first?
I will.
Okay, Carl, go ahead.
Hi, just kind of more of a kind of procedural kind of question. As you guys were building up your robot, what kind of characterization test or test program did you guys implement to try to understand what the controllers were going to look like, what they were going to work like, and how you might modify their design? No.
I'm sorry, can you repeat that question one more time, please?
Okay, so this is more of sort of like a engineering design process kind of question. And so of course the controllers and some of the mechanisms that you assembled the robot with were manufactured by other vendors. And I'm just curious, did you guys implement a characterization test program or a calibration test program in some way so that you could understand how the operating system worked, how the controllers work, and so on, and then obviously tailored that using that information, tailor that to your specific program?
So just to clarify, this project was a continued project. So the robot had the robot had been given to us already working autonomously. Our project, we had to basically implement a wireless communication and odometry system for the robot to determine the traverse path of the robot. So to answer your question, for us to use a test simulation, we did not use a test simulation to determine what scope that we would need to basically determine what electronic sensors and stuff that we would have to use. We just did as much thorough research as we could possible to determine basically what would be best fit for our needs for the project scope.
Okay. So I just to make sure I understand, you basically, well, I guess you answered the question by saying you didn't do a particular test program, but you did do research and characterize the hardware such that it could be applied to your particular effort. Would it be fair to say that?
Exactly.
Okay.
So for how we tested the IMU, we used the Arduino program and the code that was given by Bosch, and we used that code to test the sensors, the values that the IMU would produce, and we checked the values of the data, and we checked the yaw heading for the IMU, and we determined that it was accurate for our use case.
Okay.
So is that for the IMU sensor? Yeah.
Okay, good, thank you.
Yeah.
I noticed in the presentation that there looked like there were several places where you probably did some programming. Who on your team did the programming? And did you do it all in Python or what?
We did it in PSOC IDE or PSOC IDE. Yeah.
Yeah, we did the programming in C, and I was in charge of doing the mission computer, which was in Python and C. So part of the receiving side from our sensor for the RF module, the receiver, was in C, which was integrated with Python in order to display the images received from our receiver. And the Python library we used was the matplotlib and NumPy.
Okay. Was the software done by one member of the team, or did everybody contribute to the development of the software?
We all contributed certain areas. If one team member couldn't figure out one thing, then maybe another team member can input maybe a solution to our software.
Okay, thank you.
You're welcome.
Other questions?
What would you guys say was the hardest part about this project?
The radio frequency, the wireless communication, I would say.
Yeah. I would say that was probably the hardest part.
Mm-hmm. We originally had a different RF module that was actually working on the 2.4 gigahertz network, and we came to realize that transmitting data or information that we needed to obtain from our actual robot, it was almost impossible due to all of the other static and noise that was basically coming from all the other Wi-Fi routers or cell phone devices. So the data that we were collecting on the receiving end was just a bunch of gibberish. unusable data. So definitely the RF modules were difficult.
I have a question.
Yeah.
What is the range of communicating through the Wi-Fi? How far away it can be from the Wi-Fi spot?
So just to clarify, we're actually not using Wi-Fi. We're using just the RF frequency of 915 megahertz. The range that we had tested was the furthest that we had taken it to was 300 feet through about 5 brick walls. So if there is an open field completely, I'm sure we can exceed over 1,000 feet. And if there's multiple walls, I'm sure we can easily tackle 300 feet of transmission and receiving.
And now that you say that, how can you control it? Are you remote controlling it, or are you getting real, real life data?
Yeah, we are getting real-time data from the robot. The robot is actually autonomous on its own, so we have no control over it. The only control that we have over the robot is a Bluetooth implemented kill switch that, if necessary, we can kill the robot at any time if we have ever lost it, for example.
How does the robot know where to go?
So there's actually an ultrasonic sensor that's placed on top of the robot, and the robot actually has a programmed into it basically to continue on forward. So as it's moving on through its path, as it detects an obstacle, it'll either turn left or right, depending on if the left or right side of the obstacle is clear, and then it'll try and avoid the obstacle, and once the obstacle has been avoided, it'll try and go back to its original heading. So it's all done autonomously.
Okay. I'm just curious, why did you not select a GPS receiver for position location?
So this was actually one of the things that we had early on that we had discussed with our advisors. We determined that a GPS would not be practical for our use because the robot would essentially be placed inside of a building. It would not be placed outside of a building. And the communication of the GPS inside a building is really poor, extremely inaccurate, and we wouldn't get a reading at all. So we had to go with optical encoders and IMUs.
Yeah, we had to use local sensors, not external sensors.
Yeah, that in turns, that's why we also created a mission computer, which tracks the distance of the robot of the location of the robot, of where it has traveled over time.
Okay.
I have a question.
Yes.
So you guys were collecting data through C and plotting it through Python, is that right?
Yeah, that's correct.
Was there any like intermediary programs that you guys used to get the data from the C into like a bridge between the C program and the Python program?
Well, we sent our data through a serial port, and then through the serial monitor of the computer, it's being sent and read. So it's being sent in C, and it's being read through the Python IDE to be interpreted in that environment. And then it'll be manipulated based on our program in order to plot our data of a robot.
Okay, so it's basically almost a direct transmission.
Yeah.
Okay, cool, thank you.
Any other questions? Okay. Well, if not, let me thank you and the team. You did a good job. Let me thank your Raytheon sponsors for being terrific partners with Cal State LA in this.
Yeah.
It was an interesting project. I was glad to see you were able to get as far as you were. I'm sorry you weren't able to integrate the whole system together. These kinds of interruptions are actually being experienced by everybody. So,
Yeah.
Anyway, congratulations. And our next presentation is in about 10 minutes. This will be a presentation on lithium-ion battery characterization. Let me encourage everybody on the call to look for the Qualtrics survey to provide some feedback as to the presentation. The feedback will be, I'm sure, of interest to the students, and the university uses it as part of a report to the ABET accreditation board. So it's of interest to us as well.
Yeah, could I add one comment?
By all means.
Anyways, one of the things that I thought of, well, basically both John and I thought of, was, well, if they can't go ahead and finish all the hardware on the robot, do all the integration testing, and finish up the project like all the rest of the teams have, we're going to go ahead and we're going to make this an exercise in technical writing. So I had them go ahead and write up a lessons learned manual, a path forward manual, as well as a test procedures for the next team to take it from there. So I think overall, I think it's, I mean, I of course have been enjoyed working with the students, and I think they've learned a lot from us as far as technical writing goes. These last exercise have reinforced technical writing. I just wanted to add that.
Okay. Well, thank you for that comment, Bob. It's
Thank you, Professor Thorburn.
The team is lucky to have you guys serve as mentors in more ways than one. So
I'd like to make a comment also, and that is the team took the challenge of being shut down and stationary and being essentially shelter in place very well, and switched paths from, although disappointing because they had their hardware well on the way to success, they switched paths and started writing and came up with what I'd consider a yeoman's exertion to complete all the writing and get it all together for the next team. So I wanted to congratulate them on their resilience and contributions to our battle against COVID-19.
Very good.
Thank you.
thank you, John. Okay. Well, thanks to everybody. Stay tuned. The next presentation will begin in about 7 minutes. As I mentioned, it's on lithium-ion battery characterization. I'm sure it'll be very interesting, and we're seeing. Until then, we'll just stand by. If there are no questions, I think that we're about ready to go. It looks like the full team is here. So I need for one of the students to take over the screen and flip through the charts. Okay, it looks like Jesse's doing that. So welcome to Expo 220, and let me introduce to you the lithium-ion battery characterization team.
Thank you, Mike. This is Team 33, extracting lithium-ion battery characteristics. Our team composed of me, Jesse, Israel, David, Arthur, and Jaime. Our team advisor is Dr. Shaverdi. We also have a grad student advising us and helping us. His name is Min. Our current team is currently sponsored by the Cal State LA EE department. A quick breakdown of our agenda. I'm going to go over the background problems and objectives of our team. David's going to talk about the system overview and our design budget. Israel then's going to talk about the test methodology. Then we're going to have Arthur talk about the battery parameters extracted methodology. Jaime's going to come in and talk about the parameter optimization and a conclusion. The problems. So the first thing we're going to talk about is problems. Why does our team exist and what problems do we face? The first thing is lithium-ion's behaviors or performance are characterized in a data sheet. The first problem arises is that data sheet gives you limited information of the parameters and limited use of application. The second problem is that the data sheet is always for new cells. And we know that the data sheet will fail after the battery gets shelved or is being used moderately to excessively testing. That's where we want to talk about that the behavior is altered. And that becomes very important when we talk about systems that wish to be accurate and precise. Now we move on to the background. The background, why is it so important? It's because energy right now currently is in demand. LIBs or lithium-ion batteries include high energy density, high power, fast response, and low self-discharge, long cycles, and calendar life when compared to other batteries. It's very important because currently we have electric vehicles and solar energy that are currently transitioning to lithium-ion batteries. So it's suggested that we know how they behave and the duration of the life cycle. Another good example is control systems, energy management systems, and a team who is currently also working the battery management system, BMS, talks all about parameters of batteries. Next, we move to objectives. We talk about what we wish to do as a team. We want to build an apparatus that allows us to test for different things such as capacity, pulsation, high density, high stress test of a battery. And take that data out. We use electric models to modify our LIBs and determine the circuit parameters. We wish to take something that's complex as a battery and reduce it to something linear as a circuit, as seen in the figure. Next, we talk about project goals. What is our team project's goals? We want to be able to extract these parameters to build a model to show the behavior of that model. We will discuss more in depth how we use the state of charge and open circuit voltage and how it's going to give us a SOC graph or state of charge graph in which we will run in our code, our choice of math lab, and we find the best values of that circuit I showed you before, which is going to be consistent of resistors and capacitors. Next, we talk about research. How do we base our methodology on? We based it on two different findings. The first being a book that talks about advanced electric drive vehicles. And then we talk about the second, which will be the article, which talks about how to make that error margin even smaller with bandwidth. They both took the experiment-based model approach, and that's what we choose to do as well to get the best result. Now I'm gonna shift now to David, who's gonna talk about a system overview of our project.
Thank you, Jesse. Before I discuss our safety equipment, I think it's necessary to give you guys a little background on our project in regards to battery choice. During the early stages of our project, our goal was to create a system to safely extract data from a 12.6 volt battery and move up to extract data from a battery with a voltage of 60 with a similar system, which poses a lot more danger to our work than our current battery, which has a much lower voltage of 3.3 volts. And I'll explain the reasoning for the switch shortly. Our safety equipment was chosen with the expectation of eventually working with a high voltage battery. So we have protective eyewear to protect our eyes, insulated gloves to protect us from being shocked, a rescue hook in case someone does get shocked and we're able to pull them away without touching them. Some other safety measures that we took include wearing protective clothing, such as pants, long sleeve shirts, and closed-toe shoes, securing long hair or dangling accessories, daily cell inspections before testing, and last but not least, we would perform testing with 2 or more present, just in case an emergency was to occur. And now we'll move on to discuss our block diagram. So this is our block diagram. So this is our block diagram representation of our battery testing apparatus. We actually replicated this diagram from a research journal called The Accurate Battery Pack Modeling for Automotive Applications by Lee and Mazzarola. During their testing, they used a 14.4 volt battery along with a 30,000 watt power supply and a 3,600 watt electronic load. And while using all this, they produced a 0.31% margin error. First, we have our computer over on the left, along with the program LabVolt. LabVolt allowed us to track the data that was extracted using the data acquisition. Data tracked include number of sample points, time, pulsation, voltage, and current. Next, we have our data acquisition connected to the battery, along with the electronic load if the battery is being discharged. If the battery is being charged, the power supply, we would use the power supply that you can see on the bottom right. One of our future goals before the pandemic occurred that we were working toward was actually to extract data from a battery pack made up of 6 3.3 volt cells, but we were only able to test the cells as individuals only. I will now move on to go over our testing equipment. First, we have our power supply with the limitations of 5 amps, 30 volts, and 150 watts. Next, we have our programmable load with the limitations of 40 amps, 150 volts, and 400 watts. Third, we have our data acquisition and control interface, also known as DAC, with a 1 second sampling time and a limitation of 40 amps. Lastly, we have our A123 lithium-ion phosphate cell with 2.3 amp hour for cell capacity and a 3.3 volt limit. I will now move on to show you our physical setup of our testing apparatus. So we have our DAC, excuse me. So we have our DAC in the top left corner, the electronic load in the bottom left corner, which it can also be replaced with the power supply depending on if we're charging or discharging. In the middle there on the table, we have our A123 cell connected to the electronic load and DAC. In the top right corner, we have LabVolt running on the PC. Lastly, we have a close-up shot of the DAC panel. Now we'll be moving on. Next, I will go over the team's budget and expenses. We have our power supply that was actually purchased by our grad student, Min. So no expenses came out of our budget for that. Thank you, Min. The DAC that was used was supplied by the university, so no cost to us. The electronic load that was used for discharging cost $196.01. The A123 lithium-ion cells cost $12.02 each, and we purchased 7 of them, totaling in an amount of $84.20. The 3D print design of the cell housing the prototype that we created in Makerspace had an expense of $8, which left us with a remaining balance of $11.79. So as I stated before, when we first started our project, we planned to scale up from a low voltage battery to a high voltage battery, and our work can be scaled up. And excuse me, our work can still be scaled up, but due to the restraints of our budget, we weren't able to go beyond our current battery package. For a 3,600 watt power supply, it costs approximately $3,000, and for a 3,600 watt programmable load, it costs approximately $5,200. And now we'll be passing it off to my teammate Israel that will be discussing our team's testing results. Israel.
Thank you, Norman. Now I'm going to present the testing methodology on data extraction for our project. The testing objective is to determine the capacity of our battery using different C rates and methods. On figure 1, you can see our physical connection of our circuit using a power supply to input current and voltage to the circuit network.
It's our duty to find the common ground for all.
Figure 2 shows the graph or data plotted from a charging capacity test. The purpose of charging capacity test is to verify how much energy can be stored in it, taking into account the datasheet specifications. In this specific test, we start charging the battery with constant current until it reaches the cutoff voltage, and when it reaches and when it is reached, constant voltage takes place until it's fully charged. And to verify it, we use a formula C over 100, C being the C rate. At that point, we understand that the battery is fully charged. Next slide. On figure 1, you can see that we are using an electronic log to deplete our battery. This is called the discharging capacity test. On figure 2 shows the graph or data plotted from a discharging capacity test. For this test, we extract energy from the battery, but before extracting energy, we need to make sure that the battery is completely charged, as shown on the previous graph. The objective of this test is to observe the performance of the battery while energy is being consumed. For this capacity test, we start depleting the battery using 1.5 amps, a constant current until a threshold is almost reached. In our case, 2.6. Once it gets close to the threshold, constant voltage is used to finish discharging until the threshold is completely reached. The range is based on datasheet to protect the normal battery operating without the risk of over discharging and causing irreversible damage to the battery life cycle. On the next slide, I'll go over another method. Now I'm going to go over a behavioral test. We call this behavioral test, the behavioral test. The objective of this test is for modeling purposes. This test has two purposes. One is for the SOC, OCB profile extraction, and the other is for circuit parameter estimation. As mentioned, a battery post-charging discharging cycle is required for SOC, OCB profile extraction. As illustrated on figure 1, the battery was post-discharged from full SOC to about 10% SOC. We let it rest and then post-charge back to 100 SOC to extract the SOC OCB profile. The discharging and charging pulse length was chosen as 2 minutes for each interval. The battery cell was charged or discharged by 10% of SOC each time. At the end of each discharging pulse, the battery was allowed to rest for 2 minutes to observe the battery dynamics relaxation time. The SOC test range is selected to embrace the normal battery operating without the risk of causing irreversible damage to the battery physical structure by over deep discharging. These behavioral test data are really important for circuit parameter estimations. Using MATLAB, as my teammate Arthur will explain more in depth in the following slides.
Thank you, Israel. Now we will talk about the methodology behind extracting the parameters for our battery model. Here we see the main formulas and how we derive them for our final representation of the system of our battery model. First, on the top right, we again see the circuit that our battery model was based on. On the top left, we see the parameters that we must extract, shown as R1, C1, R2, and C2, which will define our simulated battery. Below that, we see the two tau values, T1 and T2, that represent the lower and upper limit of the frequency values we expect the battery to operate in. Universally, for verifying the model, these values can be chosen arbitrarily, but we chose these values to match the research that we referenced in order to have a proper metric to measure up against. Next, we see the state space equation we used to represent our system. State space equations are generally used to take a complex system such as this battery and represent them with fewer parameters that remain consistent in each state. We see here on the leftmost matrix, these are represented by the voltage across capacitor 1, VC1, the voltage across capacitor 2, VC2, and a state of charge, SOC. On the bottom right, we see a final equation derived which shows how the voltage applied at the terminal, VT, relates to the voltage measured at the open circuit, VOCV, SOC, and also how it is affected by the voltage across the capacitors and the shunt. Below this equation, we see the summation we use to calculate the total error of our experiment. On the next slide, we'll see how our hardware was factored into our simulation. This page shows how we combine the tests of our hardware team to find our parameters. First, we determine the bandwidth that we will operate in, shown previously in our tau values. Then hardware tests were performed at different C rates and resting periods. As that data was obtained, our software team created a battery model simulation in MATLAB, and we used our derived equation to relate our measured voltage to our battery model's estimate. Finally, we obtained multiple charts that showed the optimal parameters at each SoC. Below this, we see a table showing the different C rates we tested at and the hardware specification of our battery. Following this, we'll observe our results. On the left, we see the results of the parameter extraction of the experiment we referenced, and on the right, we see the parameter extractions of our experiment. Here we see we were able to extract similar profiles and how promising these results appear so far. On the next slide, we'll expand on these. Here we show the results of our tests with a 0.6 C rate on the left and the results of the 0.4 C rate simulation on the right. Included in this page is a chart of V terminal against SoC, and if this chart is overlaid onto each parameter, we can see how each of these parameters play a role in each state of defining the SoC. On the bottom, we see our calculated error of this data, which shows a 0.25 volt difference or an 8.3% error for the 0.6 C rate, and a difference of 0.15 volts or a 5% error for the 0.4 C rate test. These errors are calculated based on the raw parameter extraction so far in our experiment, and now Jaime will expand on how we were able to refine this result through our optimization techniques.
Thank you, Arthur. Next, I'll be discussing how we were able to optimize the code to identify those circuit parameters. So we had two goals in mind. First is to reduce the overall runtime. We took our algorithm to extract those circuit parameters. On average, for a slower computer, it took about 15 minutes. On a faster computer, it took about 15 minutes. On a slower computer, it took about 30. So as you can imagine, it took our algorithm debugging a long time to compute, but at the end, well worth it. The second goal is the most important. We wanted to research different algorithm techniques to optimize our code so that it can identify those circuit parameters on its own without defining a finite range of resistance. This meant that our code can compute the algorithm using the Q-error equation. The outcome are the results shown to the right. As Arthur mentioned, these are the results we obtained without optimization, shown in the red and green curve. The blue curve is the results we obtained using genetic optimization. Next, I'll be discussing future works. So our hardware team did a lot of good work this semester, but due to the pandemic, we weren't able to perform a capacity test on the battery module we constructed, shown in figure 1. Second, the software team was able to compute and derive an algorithm that was able to identify those circuit parameters using the state space equations and optimize using the genetic algorithm. More work can be done using nonlinear least squares, curve fitting optimization, or particle swarm optimization. Next, I'd like to conclude our presentation. So there are 3 achievements we were able to complete this year. The first being that we were able to create a testing apparatus for the A123 battery, shown in figure 1. Second, we were able to extract a capacity test for the 0.4 C rate and 0.6 C rate. Third, we developed an algorithm that was able to determine those circuit parameters at an error rate of 5% for 0.4 C rate and 8.3% for 0.6 C rate. In addition, we were able to optimize their code. Before I open it up to questions, I would like to acknowledge and thank our team advisors. So we had 2 advisors, as Jesse mentioned, Dr. Shiverty and Min. They are very helpful throughout the year, and in addition to their weekly meetings, they opened themselves up to resources and questions that we're able to use and develop our code and construct a working testing apparatus. I'd like to highlight one moment, which is shown here in figure 1. This was dated back in November 5th, so don't be concerned over the face pass. We just acquired our A123 battery, and we were able to construct that battery module shown before. Thank you all for tuning in, and I would like to open it up to questions.
Okay, thank you, team. So the floor is open for questions. All you need to do is unmute your microphone and speak up. Who would like to go first?
This is Jonathan Estrada's dad. I like to say they had a great presentation. Thank you, boys, and thank you, professors, for helping them.
Okay.
Thank you.
Thank you for participating.
This is Carl Salinas, industry advisor, retired Northrop. Just more of just kind of a curiosity question. Did you guys try to establish any correlation between the battery capacities? So you talked about having to tailor your project to a lower capacity or less highly performing battery. But did you try to draw any correlations or conclusions to increasing the size of that battery to the original size that you were looking at, or even larger?
So for your question, you're asking if we looked into ways of experimenting with the larger battery that our goal was to, right?
Well, no, not so much in practical terms, but maybe just using your correlation algorithms to see if you could essentially size up the battery or size down the battery, and if any correlation existed, was it in line with what you were thinking, or was it in some way an outlier or not congruent with what you would expect? I guess the crux of my question is, all those batteries work on a certain kind of chemistry, and does the chemistry change appreciably if you size up the battery to a higher capacity or higher power, or you downsize it to a lower capacity and lower power?
Okay, sorry, Israel.
So in terms of chemistry, we're using a lithium-ion phosphate battery. And we also we have a bigger battery that we have a bigger module that it was assigned for him to test, but since we didn't have the right equipment to test it, we got some equipment that was able to test this type of battery. But in terms of chemistry, we had the same chemistry on the bigger size and this size that we're using.
Okay.
And I would like to add on, if I may. Yeah. If we go back to Arthur's slide with the equation of the circuit model itself. So we couldn't scale up using the software, as you mentioned, because if you look to the left with the source voltage, it's open circuit voltage. And so our algorithm works if we're given the experimental data to perform the estimations of the circuit parameters. So without the, yeah.
Okay, all right, I got it.
Thank you for the question.
Thank you.
Okay, other questions?
So thank you guys for the interesting presentation. I had a question about this slide actually. So I see you kind of fitted the model with 3 resistors and 2 capacitors. Is there any physical significance inside the battery that correspond to these 3 resistances and capacitances? And if there isn't really a physical significance of them, would there be some benefit to fitting it with more elements or fitting it with less elements?
So to increase the fidelity of the model, you would actually increase the number of RC connections or RC networks you have in the battery model. We found this to be the most update in literature. So that's why we chose the 2 RC network configuration.
Got you, but you don't find like one resistor corresponds to electrolyte resistance and the capacitances have to do with surface area inside the electrodes or anything like that. It seems it's more of a fitting parameter, and this seems like it's a good number. It's not too much or too little in terms of fitting the data. Right. So this model actually represents the battery through the terminal voltage. There's no correlation to the chemistry. Using this model, it actually bypasses a lot of the chemistry complexities of modeling lithium-ion batteries using this given RC network. Cool.
Okay. We still have plenty of time for other questions. Now, let me remind everybody that there's a Qualtrics evaluation form. Please be sure and fill that out. The students and the university will make use of the feedback. We certainly appreciate it. If there are no further questions, let me thank the team, congratulate you on completing your project, and it was good work. Congratulations.
Yeah, that's a good paper. I enjoyed the topic. Thank you.
Thank you very much.
Thank you, Doc. Thank you. We appreciate your input.
Thank you.
Okay, our next presentation will start at 4 o'clock. That's the UPS bag restocking team. So go ahead and stand by. I'm sure that will be another interesting presentation. And we'll just stay live. I will turn the recording off, so feel free to have discussions amongst yourselves. Okay, we'll give him just another second. I thought, did you say he was just logging in?
I mean, yeah, he was here.
He said that in our chat.
He was here. He was here earlier, but I don't know what happened. I lost the internet or something. Yeah, he's here. I could start. Okay, very good. So let me welcome everybody to the Expo 2020, our first virtual Expo. This is the fourth presentation in the electrical engineering, mechanical engineering session today. We'll be going on in this session until 6 p.m. this evening. We've got full days tomorrow and every day next week. So please come to as many sessions as you can. There's a Qualtrics survey. I think you can see the address for that in the Zoom chat. You also got a link to it in the same email that you would have got the invitation to the meeting in. I encourage you to take a moment and answer that quick survey at the end of the presentation so that we can provide feedback to the students, and also we keep this for purposes of feedback to ABET for accreditation purposes. The next presentation is the automated small package sort bag restocking team. The presentation is scheduled, we've got a 40-minute window. We expect the presentation itself to be about 20 minutes long, and then there'll be a period for question and answers thereafter. So without further ado, let me introduce the bag restocking team. Thank you, Dr. Thorburn. All right. As Dr. Thorburn mentioned, we are the automated small package sort bag restocking. We're sponsored by UBS. My name is Ahmed Abdurrahman Muhammad Al-Bayed, and I'm here with my team, Maher Ibrahim Al-Musallam, Alejandro Contreras, Alan Draymond Domawa, and Leonardo Franzoso and David Villalobos. So first, we're gonna start with the introduction with Maher, then with me in the systems engineering, then the mechanical design with Leonardo, then the electrical design with David, then the navigation with Alan, then the power with Alejandro, then we'll finish with Alejandro. So I'll pass it right now to Maher to start with the introduction.
United Parcel Service is an international shipping company which is one of the well-known and appreciated package delivery brands in the world. Nowadays, UPS has become the largest company for package delivery. In fact, UPS delivers to more than 200 countries worldwide. There are 3 senior projects at Cal State LA that are sponsored by UPS to design an automated small package sort for the UPS. Bag handling, bag restocking, and system control are the 3 senior design project, and we are here to present the bag restocking project. UPS relies on human labor for long hours in their small package shop, but they decided to bring more technology for more efficiency. The main goal of this project is to stock empty bags and to zip and carry the bags when the bags are full of packages. However, our team is only responsible to develop a bag restocking unit. Since we are only responsible of restocking bags, we had to design and build an automated cart that will restock empty bags to the small package sort station. The bag restocking unit should be capable to travel a long distance in the UPS small package sort section and detect the correct tasks that need bags to be restocked, align perfectly with the correct task, and insert them empty bags at a time and return to the loading area to be prepared for new loads. The restocking cart will be controlled by a programmable logic controller that will enable it to communicate with the other section of the system to prevent overlapping. Here is a chart organizing students and faculty, including a legion, who are involved with this project. In order to develop a bag restocking unit that delivers all required capabilities, each member of the team was assigned a task and is responsible to manage it and to ensure efficient progress for the project. And now I will hand it to Ahmed, and he will talk about the systems engineering.
So as we know that every project is basically a system, and in systems engineering, we have to find a common ground for all the parts of that project. So, but first we have to know what's the end goal of that project. Therefore, let's start with the requirement. As we see here, that the requirement that we had for the project is that we need a car that can travel 100 feet, and we estimated our car to do about 150 feet, and we need a car that can restock 10 bags at a time. We need a car that can charge can charge in less than 6 hours. We managed to do 2 hours. The safety measures here, which our car can do, about, or it can detect about 4 meters ahead, and the size that we're able to manage is 55.34 and by 28.1, and the bag installation force that we managed to get is about 85 pounds, and the operation time is about 10 minutes for each cycle. So as we mentioned earlier, that our project is part of 3 projects, and but first we have to know how all these projects all work. So the whole, or like the end goal of the project is to build I would say a gantry that can that can sort the small packages and handle them. So if we can see here that the packages will come sliding, the small packages like small boxes or whatsoever will come sliding, and they will enter into these into these it's more of like a fabric bags, and each bag will go to like a certain area code. And our cart responsibility is to go and refill the empty bags in the station after the station is out of bags. And the bag handling duty here is to handle all the bags after they get or after they're done with the small packages. And the BLC team here is responsible of having the control over the whole like the automated small package sort. So as we can all see here, we have the restocking cart. So the restocking carts, or as we see here, that the bag will be hung here on those two rods, and they will be they will be enforced into this station using two linear actuators. The controller box here is the main unit that that have the control over the cart, over everything in the cart, and the cart can move in all direction easily, and it's powered by batteries, as we can all see. So here we have a chart of how the operation of the whole thing work. So we have here our restocking cart. The restocking cart will receive the BLC data or something over the Bluetooth into the restocking box. So, and the restocker will talk with the navigation to see if there is any obstacles in its way. Then it will move around. If the if it got an order to move around, it will send the data to the drive motors. If it got an order to insert the bags, it will send the data to the linear actuator. And here we, so the cart has two modes of operation, the manual and the automated. The automated is the main one. The manual one is for more of the debugging. But so here we can see the operation mode for the automated mode. So first thing first, that the power has to be up, and the manual override switch has to be off, and the card should receive a BLC orders from the other team. Then it will send that order to move it around. Then if it's done, it will send it back into the reset mode. Then it will send also an order to insert the bags into the station, and it will. And if it's done, it will return back into its location. And if any failure happen, the card will go into the reset mode, and it will alert the other teams about it. And now I'll hand it to Leonardo to talk about the mechanical design.
So for every design, we need, right here is the design that we came up with based on the parts designed from SolidWorks. Each of the parts are designed separately, and they are assembled together to form out what the restocking card should look like. And each are labeled to help give us the idea what they are and what they function. Next. And here is what the width, length, and the height of the card should be based on the top view and the side view. And right here is the adjustable top frame, and it's really new. And as you can see in the middle image, that is what the adjustable slots should look like for the top frame. And that includes for the tusk on the right side, so that it could easily adjust the height and be able to adjust it easily with the bottom frame, and it can easily be removed instead of just welding or torch cutting. Next. Now, why adjustable frames? Well, it's not guaranteed that all the UPS warehouses will have flat grounds, and the tusks on each station could be higher or lower than the card, or could be misaligned. So this will help make things easier for technicians to adjust the height of the tusks so they can easily restock the bags to the stations. Next. Now, here are the new parts that are added to restocking card, and as you can see, the actual actuator holders and the spacer plates are needed to keep the actuator in place and they're not misaligned. And the push plate is helped to connect the actuators to the push plate in a mount. And on the right is the signal lights, but those are mostly like the operational lights to help tell that the restocking cart is functioning properly, or it's like shut off or standby. And on the bottom are the designs of the control box, navigation box, and the power box. Next. Right here is what the mechanism wheels look like, and they help drive the restocker. And the reason why these are used is because they achieve omnidirectional movements by using the rollers instead of like the usual grip tires like regular wheels. And next. And this image gives us the idea of how the mechanism wheels move the cart. So they like move them straight ahead or backwards, even sideways, diagonal, or even turn around in the middle of its axis or in the rear axis or in the concerning way. And next. And right here is the weight budget chart, and we use this to take into account the weight of every component, and we even added the contingency weight just in case to make sure we get the grand total weight, and we still made it under the max weight requirement. Next. And right here is how far we made with the cart, and as you can see, it's almost exactly as the design on the left side. But due to the COVID-19, we weren't able to install the control box, navigational box, and the power box, and even the sensors. So now I will pass this on to David, who will talk about the electrical design.
Thank you, Leo. So I'll be talking about the electrical design of our cart. So there's two methods of driving our restocker. There's a joystick and PLC. Our cart consists of both, and in analyzing both methods, we can see the cost between the two. We can see that the joystick was 40 and then the PLC is 200 plus, depending on what PLC is using. The reliability of the joystick is that there's a strong signal between the joystick and the Bluetooth, as you'll see in a couple of slides that our cart is controlled via a joystick. And then there's a communication between the systems team and the cart via PLC. So that gives it a pair function between the two. And then down at this function, the joystick's operated at the user's control, and then the PLC is just operated independently between the systems team and our team. So in the joystick use for manual control, we went with the wireless method. In comparing both, you can see that the wired, the distance from which a wire is about 40 feet, and then the wireless is about 100. Our time to complete was 2 days with the wired. That's considering all hardware being put together versus the wireless at 6 hours. And then the complications with the wired system is that a cord may not extend smoothly, so it may get tangled up. Versus a wireless system, there's really no complication. There's no movement restriction as it's wireless and it's all via Bluetooth. The safety for the wire system is that the cord may pose a safety concern within the UPS warehouse versus a wireless. We have ultrasonic sensors, which I'll be talking about in a moment, where it detects the obstacles in its path. And then the maintenance durability between the two is that the cord may wear out over time and it'll have to be replaced versus a wireless system. Just has to do with the software and the hardware, and it also has greater durability. So here are our actuation components. It all begins with the microcontroller Arduino Mega, and that all branches out into further microcontrollers, which control the drive of the wheels through the driver motors and then the encoders to cause a rotation in our mechanism wheels. It also branches off into our relays, which activate the linear actuators for the push plate, as well as the light on the top of our car, which you saw a while ago on Leo's CAD drawings, and as well as the Bluetooth for communication between the controller box. So here's the controller box. It contains the actuation drivers. So the controller box is considered the brain of the cart, the center of it all. It receives the commands from the PLC system. So if you look at the box, you can see the relays, you see the Arduino Mega, the motor drivers. You have power buses right at the top of the box. And then on the right side, you have the power input as well as the left side. And the power input comes in from Alex's power box, which we'll be talking about a little bit further on in the presentation. So the collision avoidance and tracking sensors used. So the two sensors mainly used on our car were the ultrasonic sensors and infrared sensors. So the purpose of an ultrasonic sensor, it's a sensor that measures the distance of an object through a reflective sound wave of a specified frequency. So it basically detects object in its path, and then it lets the cart know if there's anything in its path. And then an infrared sensor is a sensor that senses change in color and other factors such as heat. Used for our design in ultrasonics, it detects any obstacle in the path of our bag restocking cart to avoid collision and prevent an issue, ensuring safety. And in the infrared sensors, it allows our bag restocking cart to follow and remain on an established path composed of the tape material, which Alan will be talking about shortly. So here's the wiring diagram for the internal of the navigation box. Up top, we have our 9-pin D connectors for the IR sensors. So it's a total of 3 sensors per pin. So that's a total of 12 sensors, 3 on each side. And we have down below and to the right are the 15-pin D connectors for our ultrasonic sensors, which consists of 4 sensors at each side. And then right above the right corner, you have the power terminal, which power is pulled from, and that comes ultimately from the power input from Alex's box as well. So the field of view, so if you look closely at the CAD drawing, you see ultrasonic sensors. Earlier in the requirements of what we were able to achieve, the distance is 4 meters, of which a ultrasonic sensor could detect an object in its path from the right, left, and the rear side. And I'll just go ahead and let Alan talk a little bit more about the navigation system.
Thanks, David. Hello, everyone. My name is Alan Raymond. I'll be talking about navigation and testing. First off, we'll talk about how the cart is driven. As David said, there's 2 ways to drive the cart. It's manually and automated. So in this manual control, you can see that it's composed of the transmitter, which is a controller, and the receiver, which is the restocking cart. Now, the transmitter is composed of the Arduino Uno and a joystick, which sends movement commands to the restocking cart that's controlled by the Arduino Do. Now, this Do uses those commands to drive the DC motors, and that drives the wheels to go into whichever desired direction that you inputted. And this is all communicated using RF modules. Next is the second way of driving the cart, which is the automated control. The PLC here works by the PLC team sending movement commands also to the restocking cart, where the cart reads the commands and starts the restocking cycle. Similarly, the Do drives the motors and the mechanism wheels, while it also uses these sensors to the left in tandem as the collision avoidance and line following sensors to execute the navigation through the factory floor so that the cart is properly following a path and that does not collide into any objects. Next, we'll be talking about the different sensors that we're using. So obviously we told you that we're using the ultrasonic sensors for object collision avoidance and infrared sensors for tracking sensors. And we'll see how they are being used to accomplish these tasks. So when testing the collision avoidance sensor, the ultrasonic sensor, we started by hooking up to the Arduino and testing the different data that it can receive. So we tested that it had a range of 200 to 400 centimeters, or about 4 meters, with a precision of plus or minus half a centimeter. And when we're dealing with a few meters, plus or minus half a centimeter is fairly precise and accurate enough for our cart to be used as the object collision avoidance system. And we saw that it had we measured it to have a field of view of 30 degrees. And as you saw in David's slides, we used that so that we're able to put a few of these on each side of the cart to cover the entire perimeter. Next is testing the ultrasonic sensors. I've hooked it up with a prototype test bed it was programmed to stop. It was first tested without moving on the ground, as you saw on the top figure. And then that worked as you saw the cart stopping when the object goes in the way. And then finally, we tested it on the ground where it was moving towards the wall and would stop right before it would collide, which was successful. Next, we'll be talking about the line following, and we used infrared sensors for this. How I did that was on the right side, you can see I put 3 infrared sensors in series to create an array used to detect the black tape, which we're using to, for the cart to follow. These sensors work by when there's a light reflected, it outputs a 1. When the light is reflected, it outputs a 0, and when it's not reflected, it outputs a 1. And as you can see on the figure on the left, we're using that to create an array. And the reason I chose 3 is due to the nature of the wheels that we're using. I used 3 to make it be able to create an algorithm to keep the cart in the path so that the cart doesn't scrub sideways or anything, because of the wheels are surrounded with rollers that can move freely. And that causes the cart can move in certain directions when you don't want it to. That's why we had it, we could program the correctional algorithm to keep it on track. Now this is the current testbed prototype. As you can see, that I implemented both IR and ultrasonic sensors for testing. The ultrasonic sensors are circled in green, while the infrared sensors are circled in red. The IR sensors are placed on all 4 sides of the cart so it can move in all 4 directions, while the ultrasonic sensors are just placed in the front and back. And finally, I implemented all of the things we've done with the sensors and simulated what would be the restocking cycle. As you can see, we've talked about how the mechanism wheels can actually move in all directions. We chose that due to the nature of the wheels, it's able to scrub sideways. So we just had it that to scrub sideways instead of turning, as it would save time as well. And as you can see, once it gets to the end of the line, it's where it simulates that it restocks the bag, and then it would go backwards in the same path and go to the desired place to restock the bags and continue however the PLC team programs it. Next, I will introduce Alejandro, who will talk about the power.
Thank you, Alan. So I'll be covering the power system of our cart. Our cart is powered by 3 12-volt, 150 amp hour batteries. And then we use power converters to convert the 12 volts to our secondary voltages, which are 9 volts and 5 volts. And our batteries are charged from an external power source, which is a battery charger. So this is a power distribution diagram of the whole cart. It basically lays out what all the components and the voltages they use, and also the ones that send back data to the Arduinos and the Unos. One of the main first tests that we did was to create a power budget for our cart. We tallied up at all the components that were going to be used, how much power they would draw, and then we also added a power contingency to be able to give us some space and leeway for if we need extra power. From there, we were able to estimate our watt hours that we would use, and at the end, we also still added a 20% margin just to give us a little bit of more power. Using that power budget, we were able to create this day in the life graph. So on the bottom plot is 2 6-hour shifts, which it would be like without our restocker recharging. And the plots on the top are the state of charge of the batteries. So if we were to use one battery, it basically depletes, and each of the batteries consequently deplete less. And this is how we determine how many batteries to use, because we need our batteries can't be discharged. The red line is an allowable discharge. And if we discharge the batteries below that, it hurts the batteries. So as you can see, using 3 batteries goes a little bit below the red line, but this is the worst case scenario. So it's good enough for regular use. Next, I was tasked with the power box of the cart. So this is the wiring diagram of the cart. As you can see on the bottom, the power comes in through a switch, and the red lines are the 12 volt. They connect to a voltage converter, which then subsequently gives us our 5 volt and 9 volts. And this is the power box of the cart. On the left, you have your SolidWorks schematic. There's the voltage converters. The middle, there's a fuse box. There's terminal blocks. On your right, you have a 9-pin D connector. And then on the picture on your right-hand side is the actual box built and wired. So this concludes our presentation. We assembled most of the hardware for the cart. Due to this crisis, we couldn't completely finish building. Our cart is built, but we couldn't connect everything and test it. We completed development for our guidance, navigation, and controls, and our cart met all of our major requirements. Any questions?
Thank you, team. So we've got a few minutes for some questions. Does anybody want to go first? You need to unmute your microphone before you ask the question. Ted, are you talking? We don't hear you.
There we go. Now you can hear me. Sorry about that. Slide 8. Everything in the briefing looks terrific, guys. A really nice package. We just didn't catch this while we were building it. Oh, slide 8. Slide 8. Way at the beginning. That's your requirements chart.
Yep.
And it's just a small detail, a little bit of a nit, but we got mixed units. We got meters, and we got feet and inches and pounds, but we want to be consistent on units. Right. And I think that just slipped through the cracks. But yeah, normally, so instead of 4 meters, it probably wants to be something like 12 or 15 feet, whatever it is.
Okay. Sure.
But everything else looks really good to me. I think the package is really professional. It's got all the bells and whistles that you need in a professional package, the schematics, it's got the budgets, it's got nice CAD drawings. So I hope you guys print out hard copies. So when you go to job interviews, you can throw this down and talk to the bag restocker, because you did some really nice engineering. It looks really good to me.
Thank you so much. We appreciate it.
Thank you. Thank you, Ted.
I have a question on page 25. And while you're doing that, if everybody would turn on their camera for just a minute, Hasmeek is going to want to take a snapshot of the audience. The question I have, 25. Okay, you were talking about all of the different trades associated with using wireless. Perhaps it was might have been the page before this or after. Nevertheless, you were talking about the advantages of wireless versus umbilical cords. And I see you've listed some of the concerns of the umbilical cords there. Mm-hmm. Did you consider, or was there any concern about interference, radio interference?
Radio interference for the wireless system?
Yeah.
Yeah, definitely. We talked about that, how the signal would be within the UPS warehouse, which is an enclosed facility. And what our discussion entailed was how the signals would bounce around. And so there wouldn't really be a difficulty from the signals and communications, either from the system team to the bag restocker or from the joystick Bluetooth to the cart within the UPS warehouse.
I was thinking more in terms of like there's so many different signals going around that you might have a problem with the signal to noise.
Right. With the signal of noise, we were only able to test indoor. So in the ECST building is where we did the testing. So that was without like real life signals such as cell phones or any other electronics that the UPS warehouse may have. So we didn't really get a chance to test the system where it's enclosed with a environment where there's a lot of signals going on within the UPS warehouse.
Okay.
Actually, Raymond, maybe you want to talk to the RF 224L1 capability?
So we're also using the RF modules, using that for the actual remote control. As you can see on, I talked about it in, I believe slide
32.
30, yeah. So we're using radio frequency modules. I actually tested this with a little, it wasn't on the cart, but it was on a program I wrote that it would either blink if it sent a signal, a consistent time. So I left it inside one of the transmitters inside the ECST building with like a lot of students in it. I would walk outside of the building. It was about almost across, like past 100+ feet through like the walls and all the metal and everything. And it still had a pretty good signal. So I believe that in the UPS factory, it should still be able to have a strong signal, even though there's a lot of disruptions and everything.
You know,
But it still needs,
you know how many channels it has, Raymond?
Currently, no. It's I lost out of my. I forgot how many channels, but you can connect different various channels for either transmitting or receiving, and back and forth.
It has over 120 channels. So if you collide with Wi-Fi or some other 2.4 gigahertz, you can just select another channel. That's one of the real beauties about it.
Okay. Thank you.
Yeah, it's actually better than Bluetooth, I think. It's pretty good. Yeah.
If everybody would turn their camera on for just a second so Hazmi could get a picture. I want to thank the team for participating. You guys did a great job. Thanks to Ted for his support as an advisor, and to the UPS clients for their continued involvement in the program. This has been an important project for a number of years now. I think the students get a lot out of it. Are there any other questions or comments that anybody wants to make?
I had a quick question, Mike. So I like this year how you guys incorporated some adjustment capability to meet up with the horns. Is there some issue though in that some of the, if one bag restocker is restocking 8 different sets of horns, is there, does it need to be adjusted for different horns? In the future, should your little protruding sticks maybe be able to find and adjust to the other ones, or there's not that much variation, in one set, in one row of the horns?
We have thought about that. Depending on each tusks, it can vary between each, like a lot of them, because in each factory there's like I believe there's like over 100 stations, and we thought of doing a automatic like a sensing mechanism for the tusks that can actually change and what's it called? You can change to the level of the actual tusk on the restocking cart, so that like you don't have to do it by hand, it'll do it automatically. The thing is, we still need to get into like what kind of sensors we should use in order to do that, and the mechanisms in order to do that, because we're gonna have to add more, like let's say motors or servo motors to like the actual tusk, so it can move sideways and be precise, because it needs to be precise in order to push the bags inside. So that has been brought up. This is the easiest fix as of right now with the slots, but later on maybe we can implement something that can automatically do that. Yeah.
Oh, can I comment on that? With Ted, we also talked about introducing like some kind of like camera which would detect like if we put like some red dots on the end of the tusk. But one of the problems we were thinking is it would take a lot of computing power to do that. So either we would have to implement a computer onto the cart, or figure out how that would be possible to do.
Makes sense. That sounds very cool.
Sounds like that could lend itself to kind of a separate payload module approach, where you could just, attach a module that's specifically designed for a certain configuration and trade them in and out as the configuration changes or the sizes change. That might be a way to look at it.
Right.
The good presentation though. I really like your graphics.
Thank you. I appreciate it.
Thank you.
Okay.
You guys are 41, right?
Right.
Yes,
Okay.
that's right. So by all means, everybody take a look at the Qualtrics survey and offer some feedback. We certainly appreciate that. Queued up now for the next presentation. It is 4:40. Let me just kind of take a roll. Daniel.
I can have a minute, please.
Who?
So I would like to thank our advisor. I mean, he was really a big help to us. He was always with us 3-4 times a week sometimes. He was with us in every step. So we learned a lot. I mean, I speak on behalf of myself and the team. We learned a lot from him. So we appreciate it really much, Ted. Thank you so much.
Thank you, Ted.
Thanks, Ted.
Okay.
Hey, Mike, quick, I know I'm out of time, so I just want to say thank you to this team. It was a great pleasure of mine to watch all of your hard work come to fruition with the presentation you guys put together. For those of you that don't know me, I'm Kurt McMillan with UPS, so I represent UPS, obviously. So thank you for your time, and thank you for all that hard work, and I loved what I saw, so I appreciate that.
Thank you so much. Thank you.
Thank you.
Okay. Thanks, everybody. It is time now to get ready for the next team. Let's make sure everybody's here. Somebody is Wasan, Daniel, Louis, Maria, and Bianca.
Yes. Right.
I see a few of you.
Yes, I'm here. Luis.
Sam.
Bianca.
Maria.
Maria.
Yes.
Bianca, I see Daniel.
Yes, I'm here.
Okay, excellent. You guys ready to go?
Yes. Do I just share my screen or?
What you want to do is to share your screen.
Okay.
Opening remarks, but go ahead and grab the screen as you get ready.
Awesome.
Everybody, welcome to Expo 2020, our first virtual Expo. We've got a full plate today and a full complement of presentations tomorrow and every day next week. In addition to the electrical and mechanical engineering presentations, there are computer science, civil engineering, and technology presentations running concurrently. Along with your invitation to the meeting, you got a link to an evaluation form. We encourage you to fill out an evaluation after you've seen the presentation. It's very easy to do. It's just 9 multiple choice questions. This will provide interesting feedback to the students and to the university as we try to improve our program and share statistics with our ABET accreditation folks. The presentation, we've got a 40-minute time window. We expect the presentation will last about 20 minutes, and then there should be ample time for question and answers after that. So are you guys going to grab the screen? Somebody? Okay, Luis is taking over control. Then without further ado, let me introduce to you the team that's using FPGAs to accelerate machine learning workloads.
All right. Just is the screen okay? I can't see it from my end.
Yeah, it looks great.
All right. Awesome. All right. Thank you. Okay. So hello.
I'm sorry. What team number is this?
Number 60.
60.
Mm-hmm.
Thank you. Sorry.
All right. Okay. So hello. Thank you for joining us for this year's Expo. My name is Luis, and my team's Capstone design project is using FPGAs to accelerate machine learning workloads. Our faculty advisors are Dr. Charles Liu and Professor Lin. We as well had a graduate advisor named James Velasco. The project is sponsored by Cal State LA's Department of Electrical and Computer Engineering. And thanks to Dr. Thorburn, we were able to persuade Intel to donate 2 expensive FPGA boards, which are essential for this project. Okay, so I'll continue with the agenda for today. I'll introduce our project's objectives and overall design, then follow with a description of what the machine learning algorithm CNN is. Then I'll discuss the programmatics of our project this year. Next, my teammate Wissam will elaborate on why the Softmax layer is a key calculation layer in the CNN and how we plan to implement it on the FPGA for acceleration purposes. Next, Wendy will review how we use Verilog to prototype the Softmax implementation on the FPGA in order to validate the system design concept. Next, Bianca will explain how we plan to use the lookup tables in order to avoid the complex calculations. Finally, Daniel will speak on how OpenCL was used to integrate the FPGA with the host CPU. He will as well finalize the presentation with a brief summary of the presentation and welcome questions. So for our project, we were tasked to accelerate a machine learning algorithm. The proposed solution was to send the computational workloads of the machine learning algorithm to a field programmable gate array. This is better known as an FPGA for short. And this was used for image classification. The purpose of the project was to explore the potential use of a synchronized FPGA as an accelerator and CPU system, as opposed to other popular accelerator alternatives such as GPUs. So how do we do this? We used a OpenCL framework to develop a heterogeneous system that will allow a CPU and FPGA to run a CNN that classifies handwritten digits. So there's a lot of terms going around, but before my team explains what a CNN is, what an OpenCL is, and what FPGAs are best used for, we must first be familiar with overall heterogeneous system design. So as shown in the figure, this is our final heterogeneous system design. As you can see, the system has an input and an output, the input being a handwritten digit and the output being classifications for this input. So in this case, we're classifying numbers from 0 to 9. So in the far right, you have your probabilities from 0 to 9. This image is first read by the host desktop CPU, which communicates with the OpenCL accelerator. This communication is done thanks to the PCIe connection. After doing the computational workloads, it returns the classification for each digit, or better known as classification. So in this case, our input was a 6, and our output is a 6. 6 has the highest probability, which is 81%, as opposed to the rest. All the probabilities sum to 1 because of percentages. Okay, so now I'll go over some background. Become familiar with CNN. So CNNs are one of the most common machine learning models for image classification. So a CNN essentially does the feature learning of an input. It then outputs the classification of an image thanks to the feature learning. In this example, we have an image of a car as an input. The image first passes through the first layer of the feature learning process. And this first layer is the first layer of this process is a convolutional layer, which applies a filter on the image, which results in a new image with desired features of the original image, which is the car. It is then followed by the ReLU and the pooling, which downsamples the image in order to prepare it for the classification process. The classification process includes a softmax layer, which is responsible for calculating the percentages for each classification. In this case, the classification includes car, truck, van, bicycle, etc. A well-designed CNN will return car with the highest probability. So for this project, we had 2 requirements. The first being design. The design requirements included image classification and to synchronize an FPGA and CPU system to perform the CNN algorithm. The second requirement is functional. This includes being real-time, meaning having a low latency when processing the images. This as well includes high throughput which means that it will process a large number of images, low power consumption, and flexibility. In terms of flexibility, we're using an FPGA, which allows us to manipulate hardware. Okay, so for our team, we divided the work into, first it was research, which was done in hardware, CNN, and Softmax design. But later in the year, we started to program our project. So we divided the team again in OpenCL and Verilog. So these are the steps of developing the heterogeneous system we had earlier in the slide. Steps 1 and 4, as you can see, were completed. However, the final 2 steps are stuff we did not complete. We did start integrating, for step 5, we did start integrating the lookup table, but we weren't able to complete it. And because we didn't fully integrate all the lookup tables, which you'll later learn that we had a number of them, we didn't get to the last step, which was to classify 28 by 28 images. So now my teammate Bassam will lead the discussion on results by talking about the Softmax layer.
Thanks, Luis. A softmax function is a type of squashing function. Squashing functions limit the output of the function into the range 0 to 1. This allows the output to be interpreted directly as a probability. Similarly, softmax functions are multi-class sigmoids, meaning they are used in determining probability of multiple classes at once. Since the outputs of a softmax function can be interpreted as a probability, a softmax layer is typically the final layer used in neural network functions. It is important to note that a softmax layer must have the same number of nodes as the output layer. A neural network may be attempting to determine if there is a dog in an image. It may be able to produce a probability that a dog is or is not in the image, but it would do so individually for each image. A softmax layer allows the neural network to run multi-class functions. In short, the neural network will now be able to determine the probability that the dog is in an image, as well as the probability that additional objects are included as well. In the slide, as you can see, below is the equation we used for the softmax. However, this equation has a problem in terms of implementation, which is the division and exponential calculations, because they require high amount of hardware. So to fix that, we chose a different approach. This slide shows the approach we chose, which has 3 key elements for the solution to be effective. The first element is eliminating the division using domain transformation, and also converting the division into subtraction. The second key is using lookup tables to avoid complexity of the exponential calculations. And also, finally, adding sorting blocks to reduce the numerical range. And this is going to be the softmax, the approach we follow for the softmax. And now Wendy will go over the implementation of the softmax in Verb.
Okay, so our first structure is the mux and comparator structure. This structure is responsible for finding the maximum input received by our softmax layer. This structure is composed of 3 subcircuits. We have our 2-bit comparator and our greater than comparator. These 2 structures have all inputs and compare them with each other. And our third circuit is our 2-bit mux. This circuit receives the selector bit, which is 0 if input 2 is greater than input 1, and 1 if input 1 is greater than input 2. This structure outputs the corresponding input. So this module repeats according to the number of inputs we have. Our design has 10 inputs, so we have a total of 9 sorting structure. And this module represents the W.amax in our softmax equation. Our next structure is the first set of subtractors. This structure is made up of 2 subcircuits. We have our 2's complement circuit and our addition circuit. The 2's complement circuit is composed of an adder tree, and it uses a set of SOR gates in order to flip all of the input bits and the adder tree then adds 1 bit to our value, creating a 2's complement equation. Then our addition circuit adds this negative value to all of our inputs to obtain a negative value for every input in order to reduce our exponential rate range as it goes into our exponential lookup table. This addition circuit repeats for every input, so the more inputs we have, the more addition circuits we will use. And this module is responsible for the Wm.A minus W.A max section of our softmax equation. Our next structure is the adder tree structure. It's responsible for finding the total exponential sum, and each adder tree is the sum of 2 inputs. So the more inputs enter, the more adder trees we will have to stack onto this structure. Each bit is also corresponding to a new element on the adder trees. We chose 16 bits of accuracy for the exponential sum, so our model has 9 adder trees of 16 elements each. And this module represents the summation in our softmax equation. Next, we have our final set of subtractors. This structure is responsible for subtracting the logarithmic sum and the negative differences of our inputs. The main difference between this structure and our first set of subtractors is just 1 bit due to the size of our output from our logarithmic lookup table. Some errors we have with our design are that we multiplied our values by 2 to the 10th in order to avoid dealing with binary decimal numbers. So our output is still being shifted by 2 to the 10th, and our final value will also be in logarithmic domain. So instead of outputting our final probability, we will be outputting the natural log of our final probability. Okay. And next, Bianca will walk us through the lookup tables.
So to use the simplified version of the softmax equation, we need to use lookup tables. Lookup tables are matrices that hold values and can be easily searched through to obtain these values. They are used to reduce hardware complexity by eliminating the calculations needed. As you can see in the block diagram in the upper right corner, exponential and logarithmic lookup tables are needed. The size of the lookup table impacts the FPGA memory. Ideally, the lookup table will be stored in local memory of the FPGA, so it's easily accessible to use in the softmax equation. If we were to use the lookup table in global memory, which is shared between the CPU and FPGA, then the program would run slower. The exponential lookup table will have a range of 0 to 1, and the logarithmic lookup table will have a range of 1.5 to 2.5. We wanted to design the lookup tables so they were not significantly large, but also large enough so the loss of accuracy isn't significant. So to determine the size of the lookup table, we examined Python code of a CNN. We ran this code and downscaled the data by the decimal place while ensuring the accuracy remained above 80%. We tested the decimal place starting at 1 and up to 70 decimal places. Each decimal place was tested 5 times and the average of the accuracy was taken. These results are shown in both the graph and the table. As you can see, when the decimal place is below 4, there's a large decrease in accuracy. So to determine the number of bits needed to accommodate the values to the 4th decimal place, we needed the bits to equate to 10 to the 4, which equals 10,000. Computer architecture only calculates in the power of 2, so there's no exact value for 10,000. However, 2 to the 14 equals 16,384, which would suffice for a digit to the 4th decimal place. And this is how we concluded we would need 14 bits for 4 decimal places. The only issue we did have when running this test was a runtime warning. Because we were using a logarithmic calculation, there was a chance of calculating the natural log of 0, which would return an undefined value, and this would disrupt the accuracy calculation. So when this happened, we would reset and then rerun the code, and this resolved the issue. So our final lookup table design holds 16-bit data to maintain good accuracy. And as I said in the previous slide, 14 bits would suffice, but we added 2 extra bits to take into account the overflow. A typical lookup table has a float 64 data type, which is 2 to the 48 times larger than our lookup table with only 16-bit data. This adjustment saves a significant amount of local memory on the FPGA. So this slide shows an example of an exponential and logarithmic lookup table. They each have 65,535 addresses to account for the 2 to the 16 number of data values. The low end of the exponential lookup table equals to 1 because e to the 0 is 1, and the high end of the lookup table equals 2.7183 because that's the value for e to the 1. So now Daniel will continue with some background on OpenCL.
Okay, so OpenCL is a C-based framework which provides a standard interface for parallel computing across heterogeneous platforms. That means that OpenCL allows communication between the two different hardware components. In this case, it would be the CPU on the host PC and the FPGA. In order to use OpenCL, we had to download some software. The first one being, excuse me, the Intel FPGA SDK for OpenCL, Visual Studios, and the TerraSync FPGA board support package. What is a kernel? A kernel is an entry point for passing data to and from the compute device. It's similar to a function call in a program. So as you can see in the image, we have the CPU on the host PC and the FPGA. OpenCL provides a context that allows them to communicate and pass data back and forth. Going from left to right, we can see that the program is comprised of the kernel code and the host PC code, and that forms the program. The kernel is the function call, which allows the passage of data. We have memory objects such as images and buffers. Buffers are the temporary holding of the data to be passed. And then the command queue is simply how we want to order the kernels, whether we want to execute them in order or out of order based on certain events. Just real quick, the memory that we're going to be using is global memory of the PC and the FPGA. This is where we're going to store our read and write buffers, which will hold the data as it's being passed. Next, we have constant global memory, which we're going to use to read only the flattened vector values and the weights that will be passed to the FPGA. And the local FPGA memory is where we want to store the lookup table in order to eliminate the exponential and division calculations. Okay. This is some of the kernel code that we wrote in order to do that. So for kernel A, which is the lookup table initialization, it is stored on the local memory of the FPGA. The one shown is just a simple 2x2 lookup table just to make sure that everything works. And the code on the right, which is kernel B, the Softmax layer implementation, that is, if you look at the top, you can see that the two parameters that are being passed in are constant, which is the flattened vector and the weights. And then the third parameter is the output, which is the probability that we're going to calculate on the actual FPGA itself. For this example, I put the weights on here just so that way you can easily see and tell that the weights are going to be used. Below that, you'll see the calculation that's performed on the FPGA itself for the flattened matrix and the weights. And then below that, you'll see the actual calculation for the probability. And that's the probability that will be passed back to the host PC itself. For our final results, for the OpenCL implementation, we did run into an issue when running the two kernels, that being the lookup table initialization and the Softmax kernel. When we were trying to run them on the same program, we were, however, able to run the initial Softmax layer, which included the exponential and the division. Those probabilities were calculated and shown at the bottom in the image. So you can see we have probabilities for each of the 10 digits, and the summation of those probabilities does equal 1. So we were able to execute the initial Softmax equation. The time for the total program to run was 23.985 milliseconds, and the kernel itself ran in 0.035 milliseconds. For the Verilog prototyping, we were able to run the modified Softmax equation, which eliminated the exponential and the division. If you look at the bottom at the block diagram, you can see we made it to the output of the adder tree. So that means we were able to include the exponential lookup table. So with the inputs to the modified Softmax layer listed on the slide, you can see the expected output, which is 1625. And our actual output was 1625, and that does include using the exponential lookup tables. Unfortunately, we ran out of time and we weren't able to implement the logarithmic lookup tables. To summarize, the objective of our project was to accelerate machine learning by placing some of the computational workload onto the FPGA. As you can see, we load a hand-drawn image of a 6 onto the host PC. It does run through the CNN, which is located on the host PC. And then once it reaches the Softmax layer, there's a kernel call which will send the flattened matrix and the weights to the FPGA, where it performs the Softmax calculation. So it sends back that probability information back to the host PC where the classification is made. So on the right side, you can see the different probabilities for each of the 10 digits, the highest one being 6, which is 81%, and the actual input image was a 6, so it was correct. I think that's it. And thank you for attending our presentation, and we hope to answer any questions you have.
Okay, thank you. Thank you, team. A very interesting presentation. We do have plenty of time for questions. Who would like to go first? All you need to do is unmute yourselves. Oh, questions first? Okay. Do you have like a summary breakdown of which of the different things that you were implementing gave you the most performance enhancement or improvement? Can you guys hear me?
No, I don't think we broke it down. I don't think we have a breakdown of the performance enhancement.
Do you have any sense over which one where you got the most performance improvement?
No, unfortunately, we don't. We didn't make those calculations.
Okay. So what are the next steps that need to be done? I saw your checklist where you indicated there were a bunch of things that were finished, but there were a couple of things left undone, although you indicated that you were partially completed, or you partially completed the 5th item. So how much work is left to be done?
Okay, so we're on we left off on step 5. Step 5 includes we did the analysis of the lookup tables as to how to structure them and build them. We've had working lookup tables in the prototype Verilog and in OpenCL. However, they weren't fully scaled in order to classify 28 by 28 images. If we were to classify 28 by 28 images, that requires a large set of numbers. But that analysis, the one that Bianca talked about, the 2 by 16 lookup tables would cover this. It's just we didn't get it to function in our designs.
Okay.
So trying to think a little bit, this is a little, I'm not real familiar with this technology, so bear with me if you will a little bit, but in terms of, I guess, staying on topic with kind of a path forward, are you developing, or is there a way, or should it be developed, kind of a hit list of objects or items or scripts that need to be kind of identified or characterized or learned from? So like your final demonstration was looking at the number 6, looking at a written number 6, but did you guys ever think of maybe looking at it a little more parametrically and trying to say what's the simplest item that could be identified or learned, and what are the steps to getting to more complex items that can be identified and learned?
Yes. So originally we wanted to identify more complex images, but we decided to go with handwritten numbers to do a more simpler version of a convolutional neural network. But if we
Okay.
wanted to take it to identify images like a dog or a cup, we would definitely have to add more convolutional layers to our CNN.
Okay. Okay. So that could be sort of the target of the future, right? Where because I'm thinking kind of in terms of the next team that may want to take on this project or something like it, that they
Yes.
could perhaps begin to look at what additional computing power they need to become more sophisticated or more convoluted.
Yes, so each filter in our CNN identifies features. Like one filter can look for edges, one filter can look for colors. So we would just have to add more filters to our CNN to identify more images.
And is there a practical limit to that?
A lot of this is under experiment. So it's not a set number of convolutional layers that you should have in each CNN.
Did you find that you had any hardware limitations, or did you have everything that you needed?
The only thing we were missing was a desktop, so I had to use mine and just bring it back and forth to and from school. That was the only real limitation in terms of hardware. So I had to use my own personal desktop.
Yeah.
But in terms of for running the actual CNN, no, there was no limitations.
What kind of desktop did you use?
Just mine that I built here. It's just an, I believe it's an i5, just Intel.
Is it Linux or is it operating Windows?
No, it is Windows, yes.
Windows, okay. Other questions from the audience? Okay, well, this was I thought, a very interesting presentation. I've been kind of watching this team throughout the year. It's a very interesting topic. So congratulations on the good work. Thanks to your advisors and certainly I don't think there's anybody from Intel on the line, but we owe some appreciation to them too. If there are no further questions, be sure and look up the Qualtrics survey and provide the students some feedback. Our next presentation is on artificial intelligence for Internet of Things devices, and that will start at 5:20 sharp. So that'll be the last presentation in the electrical engineering, mechanical engineering section today. So please stand by and we'll get started again in about 5 minutes. Okay, everybody, welcome to the Expo 2020, our first virtual Expo. We're about to have the last paper of our session today, but there are concurrent sessions in computer science, civil engineering, and technology ongoing. I encourage you to look at the entire the schedule for all of the presentations. You'll find that on the invitation that you received to attend. We also will have electrical and mechanical engineering papers or presentations tomorrow from 2 until 6, and then every day next week from 2 until 6. Each of the presentations are on 40-minute intervals. And we expect the presentation to last about 20 minutes, so there'll be ample time for questions and answers after it's completed. We have an evaluation form. It's a Qualtrics survey. You have the link of that with your invitation. I'll post the link on the chat room here. And if you don't have it later and need it, just ask me for it and I'll send it to you. We welcome your feedback on the presentations. The students will benefit from it and the university will use it with our ABET accreditation activities. Okay. Without any further delay then, let me introduce the Artificial Intelligence Server for IoT Devices team, sponsored by Saya Smart Water Management Company. Okay.
Okay. Thank you. Juan. Okay. Hello, everyone. My name is Juan Garcia. I am an electrical engineer specializing in computers.
Hello, everyone. My name is Pedro Alvarado. I'm also an electrical engineer with a specialization in controls.
Hello, everyone. My name is Angel Enriquez. I'm also an electrical engineer with a specialization in computers.
Hello, everyone. My name is Oscar Gomez. I'm an electrical engineer with control specialization.
Our project name is Artificial Intelligence Servers for IoT Devices. For those who do not know what IoT stands for, it stands for the Internet of Things. Our sponsor name is Saya, and our two advisors are Dr. Charles Liu and Professor Mo Zhang. This is what our agenda will be consisting of. First, Angel will be giving a brief introduction of the project. Angel will then jump into the algorithms, which he will be talking about the support vector machine. Pedro will be talking about the k-means clustering, and Oscar will be talking about the decision tree. I will then be talking about the Internet of Things device and the conclusion.
Thank you, Juan. Okay, so I'm going to give a brief introduction to our project before we get into the algorithms and the IoT device. Okay, so a quick background about our sponsor. Saya is a company that specializes in water management. Now, in the project that they assigned to us, it included pipes, sensors, a gateway, and a server. As you can see in figure 1, Saya set up sensors on pipes around a specific household. These sensors would then take information that includes water pressure, water temperature, and water flow. The sensors around the household would then send the data to a gateway. The gateway would then receive the data and send it to a server, in this case, an AWS server. Saya then wants the server to send the information to the owner of the household in order to inform him of anything important regarding water usage. Okay, so our objective for this project was to create a program to analyze the data from the sensors using machine learning algorithms. Now, these algorithms will automatically identify any anomalies in the data and identify whether or not those anomalies are leaks. This will allow Saya to inform the owner of any leaks and hopefully prevent any large damage caused by the leaks. Now, to give the project a more physical component, as this is mainly code, we decided to build an IoT device in order to run the program and output the results. Okay, so because our project mainly consists on machine learning, here is a layout of the process. So it begins with taking in raw data. The data is then taken by the programmer and processed and prepared. If you notice in this section, there is a loop. This is because in order to avoid any wrong results, the data must be prepared, must be very prepared. So after the data is properly prepared, the programmer would then apply algorithms. And the programmer would then use the algorithms to select a candidate model. Now, if you notice, there is a loop in this section as well. This is because it takes a lot of trial and error in order to get the right algorithm and the right model. After the right model is chosen, the programmer then deploys the model in order to make sure that the correct result is given, and then use the chosen model to use it in any application that the programmer assigned it to. Okay, so for our project, we stopped at, we were able to get to this section as we were still doing trial and error with our algorithms. We will get into more detail as we talk about our respective algorithms. And speaking of machine learning, there are two types of algorithms that we believe were useful for this project, supervised and unsupervised. For supervised algorithms, the programmer had to set parameters as the algorithm learns based on past behavior. And it also classifies data based on regression. Unsupervised, on the other hand, there's no need to set parameters, and as the algorithm learns from patterns and unlabeled data, and it classifies data based on association. Okay, so once we knew the objective of the project, we met and decided what language to use to write our program in. We decided to go with Python. So as a result of choosing Python, we wrote the code in Jupyter Notebook as it reads Python, and it also has libraries such as pandas and sklearns, which will help us for our project. And as for the IoT device, we decided to go with a Raspberry Pi 4. Okay, so once we had our resources, we met with our advisor, Professor Mozang, and he helped us assign tasks to each member. We had 4 members. So three members were assigned to research algorithms to write the code in, and the 4th member was assigned to work on the IoT device. The 3 algorithms that we were working on that we decided were best were support vector machine, or SVM, k-means clustering, and decision tree. Okay, so I'm going to continue with the first algorithm, support vector machine. Okay, so support vector machine, or SVM. So SVM is a supervised algorithm, which means it requires the user to set a parameter. SVM has a formula that converts the data into a higher dimension. It separates the data with a vector set by the programmer. This is the parameter set, and it predicts which side of the vector new data will be located in. To give you a visualization of this process, here are 3 figures. In figure 1, you can see 4 red dots. This symbolizes or represents original data, as you can see here. It is in 1 dimension, and once the SVM takes this data and applies the formula, it will change it to the data seen in figure 2.2. The data will be now in 2 dimensions, and you can see they're more spread out. And once the formula is done, in figure 2.3, you can see that the vector then separates the data into 2 groups. This vector is set by the programmer and is the parameter. Okay, so how would this help us? Well, it will help us identify leaks. More specifically, it will help us distinguish between normal data, anomalies, and leaks. This is because we have to keep in mind that not all anomalies are always leaks. For example, washing your hands, taking a shower, or watering plants. These actions could change water pressure, making them anomalies in the data. But of course, these are okay and are not considered leaks. So going back to the visualization, we can see here that, let's say the red points represent normal pressure, the green points represent leaks pressure, and the purple represent washing your hands pressure. We want to separate the leaks. However, we want to keep washing the hands and the normal pressure, as those are okay to use. In figure 2.6, you can see that the formula changes it into two-dimensional dimension. And in figure 2.7, if the correct parameter is set, they'll rate the data, the normal pressure and washing hands, and the leaks, correctly identifying the leaks. Now for our results. I was able to remove all the unwanted data and prepare the data. I select the parameters for pressure. I use sklearns to use the SVM formula, And for the normal water pressure, I actually set it to above 60 PSI. And I put the leaks will be considered anywhere between 0 to 59 PSI. Now, I did receive some reading type errors, different data types. However, this is a syntax error, and this doesn't affect the SVM process. So SVM could still be a good algorithm to run for this project. Okay, so this concludes the first algorithm. I will now pass it on to Pedro to talk about the next algorithm.
Thank you, Angel, for your presentation. I'm going to continue on with the presentation, talking about K-mean clustering. Basically, I'm going to give you an overview about K-mean clustering. The first thing is that K-mean clustering is an unsupervised learning algorithm, which means that we have only the input data, which is the X variable, with a corresponding target variable or prediction or output. It means that we only have the input, but we are not expected a label output. This is very suitable for many type of data, which means that we can work with float data types, with the string data types, but most importantly, we can work with timestamps. That was one of the features that of the reading from the data set that we received from our sponsor. It's very low on computational complexity, which means that it takes very, very few space and very few time to run. The aim of the model is to underline structure of the data in order to learn from the data and identify the group of data, which is called segments or clusters, as the name of the algorithm goes. Basically, it finds the similar characteristics or behaviors on the data set. K-mean clustering approach. Basically, the first thing that we need in order to apply the K-mean clustering is to obtain the data. We were given a data set coming from SIA, which consisted of 6 months of readings from the sensor that was placed on the household. After we obtain the data set, we also need to apply what is called the elbow method. Basically, what this does is to find the best K. K stands for the number of clusters in our algorithm. And basically what it does is that it runs an Euclidean distance and finds the closest distance between them. I'm going to talk about the K-mean clustering approach. As you can see on 3.4, there is iteration 1, 2, 3, and 4. On iteration 1, there is stars and there is dots. The stars means the centroids of the clusters. The yellow and red points means the X variables coming from the data set. The very first thing that the algorithm does is to place the centroids of the K cluster named C1 all the way to CK at random locations, and also computes the number of X variables coming from the data set, applying the Euclidean distance. As you can see on iteration 3, then the algorithm starts applying the cluster minimum distance, and then it recalculates the distance between the centers and the data set. Iteration 2 and 3 is being done until there is no more changes, and then the algorithm stops. After giving you the approach of the K-mean clustering, we have to apply it into our data set. On the slide that you see, we have the result of the data set. The very first thing that we did after we applied the feature engineering, which was cleaning the data and erasing any unmeaningful data, we ran the elbow method. It came out to be that our best K for our algorithm was 2, as you can see on figure 3.5. After we got our K, we input that K into our algorithm itself, and we chose 2 main features, which was the supply water pressure on the y-axis and the flow of the water, which is plotted in the x-axis. We have 2 clusters, which is expressed in green and red. Most of the data fell into the cluster number 1, which is the green dots that you see on the picture, and some data set fell into the cluster number 2. If it were to be an anomaly, there will be another data plot outside this red and green, and that will be considered an anomaly. But in terms of the data that we receive to train our model, we just receive parameters that were considered normal. This is all I have to mention about the K-mean clusterings. And now I'm going to pass it on to my fellow engineer, Oscar, who is going to be talking about decision tree.
Thank you, Pedro. So I'm going to be talking about decision tree. So to give you an overview about decision tree is a supervised learning algorithm, which means that it requires the user to set several parameters. These parameters can influence the output result of the algorithm. The user can manipulate the sample percentage of data utilized to train the algorithm, the minimum number of branch-off splits that the tree will contain, and the minimum number of leaves. The algorithm clusters data based on comparison of entropy within the data set. Entropy is a probabilistic mathematical calculation which can be seen in equation 1. In this equation, P sub I is the proportion of samples that belongs to the class which is represented by I, and S would be the user's input. We took the decision tree approach with the idea of clustering data and isolating outliers. By isolating outliers, we would determine the abnormal behavior on water consumption, and these events would then be looked at for potential leaks. Now, in figure 4.1, we can see a graphical representation of a node. A node is a point where a cluster of data takes place and a comparison of the characteristics is made. After the decision is made, the data can then split into smaller subsets. Now, figure 4.2 is a graphical representation of the sample data provided by our liaison. This graphical representation contains the 3% sample data with a minimum branch of 7 branches and a minimum amount of 2 leaves. These parameters were specifically chosen to keep the image from getting smaller and for the user to be able to see a little bit more clearly, since the sample data that we were provided was over 300,000 data points. The more data that is implemented would make for a smaller tree and a smaller visual. At the top node, the top node is known as the root node. This is where all the data input is initially clustered. This node will contain the most impurities in comparison to the remainder of the nodes. After the entropy is calculated and compared, the nodes are going to branch off into what is known as the tree branches. As the comparison continues to be made, the data impurity is going to change. Along with the data impurity change, the color of the node will continue to change. Eventually, the data impurity will, the data impurity will not have, sorry, I'm nervous. The data impurity, the entropy within the data set will have no difference, and the node will not branch off any longer. So this will conclude my this overview of decision tree. Now I'm going to pass it over to my fellow engineer, Juan.
Thank you, Oscar. Now I'm going to be talking about the Internet of Things. Okay. The idea behind the IoT device is to allow the user to monitor the water consumption patterns remotely from an internet-connected device. With that being said, now I'm going to be talking about the overview of how we implemented our algorithms with an IoT device. The IoT device that we decided to use was a Raspberry Pi 4. We also used a 7-inch display. We decided to design a graphical user interface written in Python, where we can give the user a better understanding and visualization of our algorithms. Like you could see in figure 5.1, that's our final GUI. For the setup, we had to integrate the Raspberry Pi 4 with the 7-inch display. We had to make sure that the Raspberry Pi 4 was running in the operating system Raspbian. We were then able to design a GUI. The integrated development environment that we used was Downy, and the important library for this GUI is Takinter. Two additional libraries that were important for this GUI were Pandas and Matplotlib. Pandas allows us to do data analysis and manipulation. As for Matplot library, this library allows us to plot data. In 5.2, you can see the setup, which is the Raspberry Pi 4 and the 7-inch display. Okay, for this GUI, we added widgets. Widgets are a user interface object in GUI. For example, buttons and scroll bar. For this GUI, we decided to use buttons. As you can see in figure 5.3, we have 8 buttons. One, you can see it says average. We have data plot, algorithms, variance, standard deviation. Also, this GUI allows us to import CSV files, and it could also save the result data, and you could exit the program. I will continue to be talking about the conclusion. To summarize, we set out to find the best algorithm that would help us analyze data of water consumption behavior. As you can see on the algorithms we have some pros and cons. For support vector machine, one of the pros is that it can distinguish between anomalies and leaks. One of the cons is that it's supervised, therefore the programmer must set parameters. K-means, one of the pros is that its training stage takes place in real time, and the cons is that it has small variations in data and can result on biased results. For decision tree, one of the pros is that it can take small samples and can be combined with other decision techniques. And one of the cons is that it's possible for feeding complex outputs and requires more processing power. Our program would then use support vector machine that would help our sponsor detect water leaks and control water management. Okay. Although significant progress has been made on the modeling, analysis, and the optimization of the algorithm, there's still work that needs to be done with this project. The complexity of the AI requires time and careful analysis, as it is heavily based on repetition along with the trial and error. This concludes our presentation. Thank you all for your time, and now we're opening for any questions.
Thank you.
Thank you, Pedro, Oscar, Juan, and Angel for the presentation. Thank you very much for all of the hard work during these difficult times.
Thank you.
Thank you.
Thank you.
How would your method determine For instance, in the summertime, we use a lot of water to water our grass, and you can see it on your bill. And in the wintertime, when we turn our sprinklers way back, we don't use nearly as much water. So does one of the algorithms take into account the time of the year or something to, anyway, you understand what I'm asking.
Yes, we do understand. Basically, one of the data categories that was provided to us was water temperature as well. So based on the water temperature, we would be able to determine the time of year, or at least it would give us an idea of, you know, when this water consumption is taking time at that given temperature. So the programs are pretty much supposed to learn through, train through previous behavior. We did not explore with the temperature because we just wanted to focus on the flow rate and water pressure, since it would be a prototype. And then in the future, the project can expand into other data sets that are provided through the data samples collected.
Okay, thank you.
So this is Carl Salinas. I'm trying to formulate a question here. I guess I may have missed it, but how did you begin to develop the requirements, or how did you look at requirements in reference to what algorithms you were eventually going to look at? What was the criteria, the kind of the requirement criteria for how you then selected the three algorithms that were investigated?
Well, when we found the objective, we just thought about it. We saw that we needed to identify leaks, and leaks show up in anomalies. So we actually just researched any algorithm that kind of like separated any anomalies from like normal type data, since we did identify that leaks were going to be classified as anomalies, since they're not really normal and they do change the water pressure. So,
yeah, but I mean, but there's a difference. There's a difference in sort of magnitude, right? I mean, the amount of pressure change in you know, when you turn on a kitchen faucet is real different than when you turn on a fire hydrant. So did you look at any sort of magnitude kind of level criteria that would then kind of point you to an algorithm that was perhaps a little bit more precise versus, you know, something that would be used on a more kind of gross or large scale? Or does it matter?
Well, the SciS product in general is going to be a household product. So the pressure is pretty much, there's going to be minimal difference. Where you're not going to see a significant jump from turning on a shower to opening a fire hydrant. I would say maybe filling up a pool. And then these were the events that we were looking to classify and define as anomalies, even though they might not be leaks. Something like filling up the pool on the summer, it would still, we would still want to classify them to bring the attention to the user.
Okay.
I have a question. I mean, there's sometimes there's a leak, like a pipe burst, and so that you've got just water spraying all over the place. Sometimes it's just like a solder joint or a pinhole leak, and it's not putting out a high volume of water, but it just never stops. What type of leak were you hoping to classify? Or were you thinking about different manifestations of a leak?
well, I don't know about my in my other partners, but when I was looking up in my algorithm, no, I didn't. I just classified leak as something that I think in my slide I said like 0 to like 59 psi. So anything that would like lower the normal water pressure, but as like in terms of like the types of leaks, no, we did not.
Well, something like that would be it would be tracked through the constant water flow. So if you have a constant water flow and it never stops, which would be the flow rate category, then that will let you know that there's something going on. And this happened when we did a visit to Saya. They told us a story about somebody who had a leaky toilet, and they didn't know about it until they installed their water meter. That it was minimal amount of water dripping, but the flow rate never stopped. It's very, very small. And that's how he was able to determine that he had a leaky toilet, and they were able to fix it. And this would be with the current system that they have right now.
I had a very expensive repair about 2 years ago that was just a pinhole leak in a pipe that went on for months undetected. And the amount of damage behind the walls and the mold, it was a disaster. So.
Yeah. Well, that was a little of the crux of my question, because I think that the way it's done today is sort of just a gross way of doing it, right? You either see the water damage, or you see a big a high water usage, and you sort of, you make a deduction. It's like, oh, I got a water leak somewhere, right? And with the kinds of water meters that they have today, you can kind of determine how much water you're using in a 24-hour period. But I guess I would challenge the team to then look at their own requirements and how they were trying to develop their algorithm to say a more accurate, or perhaps a quicker way of determining if you have a problem is to look for those kind of minute water pressure changes. And I recognize household water isn't very clean when it comes to water pressure. I mean, it fluctuates throughout the day all the time. But I think that would be a much better approach than just letting things leak until you got, 40 gallons of toilet water going down the drain every day, because that gets expensive.
Yeah.
Anyway.
So just real quick for Pedro, you had that one red cluster dot up at 30,000 PSI. Was that given to you as some data?
Well, this is the beauty about the machine learning. Basically, when we were doing our pre-processing data points, we found out that pressure that you see there was completely out of the range.
Okay.
And that's something that we were able to drop when we did how is it called, when we do the feature engineering, and we were able to drop all of those values that were meaningless. Like, for example, because you're not going to have a supply water pressure that is that high. But we actually informed Saya about this, and they found out that there was a glitch into the sensor that was reading, because we cannot have that much.
Right.
Mm-hmm.
Yeah, and a lot of data science is.
Yeah, basically the supply water pressure will range between 0 and 90 psi.
Right, and a lot of data science is just making sure you have clean data to present to the learning algorithms.
Yeah, exactly. So that's something, some of the steps that we took before actually applying the algorithm, because like we said, machine learning is about teaching the machine to learn based on the data, the data patterns, the data behavior.
Data has to be decent.
Mm-hmm. So up to the point that we stopped our project, we still need to do something that is called parameter tuning, because like I said, this is still on the stage 2. We still need to actually implement our model into more data, because the more data we give to our algorithm, the better it understands the patterns that we are aiming to describe or to find out.
In theory, yes.
Any other questions?
Good paper. Interesting topic.
Very interesting topic.
We found it really interesting because when we started, this was a complete new topic for us. And being honest with you, in these 2 semesters since we started our senior design project, we start with -0, with -0 knowledge, and along the way, we have learned a lot. Professor Torun, he's been a witness of us struggling, going back and forth, asking for opinions, asking for suggestions. And I can conclude and say, this is pretty much a good experience. And maybe in the future, I can be a data science if I continue with this project on the next level.
I have a comment. So my name is Ahmad Al-Ubaid. I'm a student here and I actually work inside Alive. I'm really happy with the stuff that you have done, guys. I'm not part of the IoT. I'm more of like a hardware guy, but the stuff that you guys have done is really amazing. So we really appreciate it.
Thank you.
Thank you, Ahmad.
No problem.
Yeah, I'd like to say this is actually the second year SIA has been involved with the program. So they're a startup company out of the LA Clean Tech Incubator, and they've been great to work with.
I would like to get a minute of your time. If you can please give us your feedback in the survey that is on the chat session, we really appreciate it, because I mean, we are open to get feedback, to get, well, there is good comments, bad comments, but we are open to all of that, And that's the way you learn from your mistakes, learn from the past data to apply into the future data.
Absolutely.
Any other question? Any other suggestion? I don't know, we are open. We still have like 3 minutes. Or.
Okay, well, thanks.
Thank you. Thank you, Pedro, Oscar, Juan, Angel. Thank you very much.
And Charles and Mo as the advisors. We appreciate that.
Yes.
This concludes our electrical and mechanical engineering presentations today. We'll pick back up at 2 o'clock tomorrow afternoon, but there are also presentations in computer science, civil engineering, and technology. I encourage you to take a look at the broader calendar. There are many presentations of interest across the college. Okay.
All right. Thanks, guys.
Thanks, everybody.
Thank you, Mike.
Bye.
Thanks, everybody.
Bye-bye.
Bye-bye.
Bye.